büyük ve değerli hocamız Profesör Doktor Feza Gürsey'i anmak üzere bir araya gelmiş bulunuyoruz. Hepiniz hoş geldiniz. Feza Gürsey yalnızca bir teorik fizikçi değil, aynı zamanda bilim dünyasında evrensel bir ışık olmuş, sınırları aşan bir dehadır. Hatta biraz evvel annesinin bir dizesini bize Burcu Hanım okudu. Ben biliyorum ki edebiyat tarafında da şairliği, yazarlığı olmasa da korkunç bir derinliğe sahip eleştirmendi. Bunu da çok kişi bilmez. Onun matematiğe ve fiziğe duyduğu derin sevda, ayrıca yalnızca akademik başarılara değil, insanların ortak bilgi mirasına katkılarla da taçlanmıştır. Robert Oppenheimer'ın da dediği gibi, yaygın ve geniş bir şekilde cana yakın tam bir fizikçiydi. Tam bir fizikçiydi. Bu yönüyle hem bilime hem de bilimin ruhuna ilham verdi. Üniversitelerimiz olarak bu topraklardan çıkmış böylesi kıymetli bir bilim insanını genç nesillere tanıtmayı ve onun izinden yürümelerini teşvik etmeyi bir görev addediyoruz. Bu amaçla bugünkü etkinliğimizde yalnızca Feza Gürsey'in bilimsel mirasını değil, aynı zamanda onun tevazu, merak ve azimle yoğrulmuş olan felsefesini de konuşacağız. Bugün bizlerle olan, dünyanın farklı köşelerinden gelen çok kıymetli bilim insanlarına da teşekkür ediyorum. Bir konuşmacımız Amerika'da şu anda. Hocam, iki konuşmacımız Amerika'dan katılıyor. Bir Koreli hocamız burada, Azerbaycan Türk'ü bir hocamız burada, yine Türk hocalarımız burada. Bu hocalarımızın, Tekin hocamız burada. Tekin Hoca ev sahibi saydığımız için ayrıca ismini yapmadım. Onların katkılarıyla bu anma günü sadece bir hatırlatma değil, aynı zamanda yeni fikirlere, yeni işbirliklerine, yeni umutlara ve gençlerimiz için yeni kariyer patikalarına da bir kapı aralayacaktır. Bu vesileyle Feza Gürsey'in ışığının genç zihinlerde sonsuza dek parlamasını diliyor. Hepinizi saygı ve sevgiyle selamlıyorum. Değerlerimizi bilimde olsun, sanatta olsun, düşünce alanında olsun değerlerimizi onurlandırmamız çok önemli. Eğer biz değerlerimize değer verirsek o zaman ülkemiz daha yücelecek. Bu yolda ilerleyen gençlerimize bir örnek göstermiş olacağız. Yani gençler bizler nelere değer veriyorsak ister istemez oraya doğru yönleniyorlar. Eğer biz hani şu anda toplumumuzun önünde olan öz değer olarak değil de popülarite olarak toplumumuzun önünde olan birçok kişi var kategorik olarak. Gençlerimizin önüne bunları koyarsak gençler oraya doğru yönleniyor. Gençlerimizin önüne değer verdiğimiz bireyler olarak Feza Gürsey gibi isimleri koyarsak ister istemez onlar da o tarafa doğru, bilime doğru yönlenecekler. O yüzden OSTİM Teknik Üniversitesi'nin diğer iki köklü ve değerli üniversitemiz, bizden çok daha değerli, çok daha köklü iki üniversitemiz Boğaziçi ve ODTÜ ile birlikte bugün yapmaya çalıştığımız şey esasında bir vefa örneğini ortaya koymak. Ama o vefa ve o değeri ortaya koyarken de biz esasında gençlerimize yeni kapılar açmayı hedefliyoruz. Sanıyorum İranlıların ya da İran Türklerinin bir sözü var. Farsçasını yapamayacağım ama geçen gün bir arkadaş bize yapmıştı. Diyor ki mücevherin değerini ancak kuyumcu anlar. Sokaktaki bir insan mücevheri verdiğin zaman mesela pırlantayı verin, sokaktaki bir insan ona değer biçemez. Hatta camdan ayıramaz bile. Mücevherin değerini ancak o değeri anlayabilecek kapasitedeki insanlar anlayabilir. O yüzden biz de bugün Feza hocamızı değerini ortaya koyarak ve bizden sonraki nesillere de bu değerleri birer ışık gibi önlerine koyarak gençlerimize de yön vermek istiyoruz. Diğer taraftan da tabii kendi değerlerimizi ne kadar yüceltirsek ülkemizde o kadar yücelecektir. Bunları gerçekleştirmeye çalışıyoruz. Hepiniz hoş geldiniz. İnşallah faydalı bir toplantı olacak.
Sayın Rektörümüze çok teşekkür ediyoruz efendim. Ben öncelikli olarak birinci oturumu sizlerle paylaşmadan önce bugün gerçekleştireceğimiz ikinci oturumla ilgili de bir bilgi aktarmak istiyorum. Aradan sonra gerçekleştireceğimiz ikinci oturumumuz modern bilimdeki son gelişmeleri konuşacağımız bir oturum olacak. Ve oturumdaki konuşmacılarımız az önce Sayın Rektörümün de dile getirdiği gibi yurt dışından bağlanacaklar. Ve ekrandan onları video konferans yöntemiyle izleme fırsatı bulacağız. Efendim, etkinliğimizin birinci oturumunda bilimin ışığında geleceği düşünmek konu başlığıyla sunuşlarını gerçekleştirmek üzere izninizle sahneye konuşmacılarımızı davet etmek istiyorum. Bugün bizlerle beraber olan çok kıymetli hocam, Koç Üniversitesi'nden Profesör Doktor Tekin Dereli'yi öncelikle davet etmek istiyorum. Konu başlığı fizikte kuaterniyonlar ve aktonyonlar ve süperkütle biçiminde çarpışan dalgalar. Lütfen hocam. İzmir Yüksek Teknoloji Enstitüsü'nden doktor öğretim üyesi Hee-Sung Zo. Buyurunuz efendim. Konu başlığı evrenin doğumunda termal enflasyon. Ve bugün şu an bizimle beraber video konferans yöntemiyle katılacak bir diğer konuşmacımız Kapadokya Üniversitesi'nden Profesör Doktor İskender Öksüz. Konu başlığı Gürsey'li hatıralar. Sizlerle birazdan video konferans yöntemiyle de kendisi bağlanacak. Ve kıymetli hocam, OSTİM Teknik Üniversitesi Rektörümüz Profesör Doktor Murat Yüle'yi de tekrar davet ediyorum efendim. Konu başlığı New Haven, Yale Üniversitesi ve Gürseyler ile hoş anılar. Buyurunuz efendim. Evet, ben o zaman kürsüyü Sayın Hocama bırakmak istiyorum. Profesör Doktor Tekin Dereli sunuşlarını gerçekleştirmek üzere kürsüden buyurunuz efendim.
Ben oradan kontrol edebileceğim değil mi?
Tabii hocam, buyurun. Sağ olun. Gerekse bu tarafa doğru tutun hocam.
Peki biraz Türkçe başlayayım ama konuşmamı İngilizce yapmam söylendi. Yani Türkçe de yapabilirim, İngilizce de yapabilirim. Şimdi bir program söylediniz, İngilizce konuşmaları Türkçe'ye çevirecek diye. Benim için de ilginç olacak. Kendim Türkçe konuşsam ne konuşurdum? Şimdi İngilizce konuşacağım, nasıl Türkçe'ye çevirecek acaba diye bir karşılaştırma yapacağım sonuçta. Quaternions and Octonions and Physics, Feza Bey'in çok tanındığı konu. Colliding Waves and Supergravity, that's my subject. Benim çalıştığım ve son makalelerin olduğu konu. Bunun da ne olduğunu sonradan geleceğim. Tam olarak bu adam nereden çıktı şimdi derseniz, çok tanıtım yapmadığımız için ben kendime şöyle bir çok kısa olarak özgeçmişimi koyayım. Benim için burada en önemli olan şey, ben Ankara Fen Lisesi'nin ilk mezunlarındanım ve de direkt olarak ODTÜ fizik bölümünden diye sandım. Master yapmadım, atladım, doktora yaptım. Yine ODTÜ fizik bölümünden doktora yaptım. Ve bu arada da doktora tezini ben doktora tezi çalışmamı Amerikalı bir karı koca genç fizikçiler, teorik fizikçiler ODTÜ'de bulunuyorlardı ve ben onların tek öğrencisiydim ve onlarla beraber doktora çalışmasına başladım. Doktoramın son senesinde mikrofon, ben bir şeye alışım, bağıra bağıra konuşmaya alışım.
Hocam isterseniz.
Ben büyük amfilerde bağıra bağıra ders vermeye alışık olduğum için gene öyle gidiyordum ama tabii daha iyi. Ses kaydı yapacak herhalde. Evet. Tamam. Tamam, sesim geliyor mu?
Yok, henüz mikrofon açık değil.
Tamam. Tamam, herhalde şimdi daha iyi ses kaydını yapacak. Doktoramın son senesinde Yale Üniversitesi'ne gittim ve doktora tezimi, ilk makalelerimi Yale Üniversitesi'nde yazdım. Dolayısıyla Feza Beylerle, Suha Hanım'la, Yusuf'la çok büyük yakınlığımız ve oradaki öğrencilerle çok arkadaşlığımız oldu. Dönüp Türkiye'ye gelip doktora aldıktan sonra beni kesmedi ki hemen ardından ben postdoktora bursu alıp TÜBİTAK'tan süpergraviti öğrenmek için Brandeis Üniversitesi'ne bir seneliğine gittim. Süpergravitiyi keşfeden genel relativiteci Stanley Dezer'in postdoku oldum aynı sene. Ve de herhalde çok iyi öğrendim ki ertesi sene beni Viyana Üniversitesi Teorik Fizik Enstitüsü'ne çağırdılar. Orada süpergraviti dersleri vermeye çağırdılar daha 30 yaşına gelmeden. Sonra 2 senede İngiltere'de Lancaster Üniversitesi'nde Research Fellow olarak çalıştıktan sonra ODTÜ Ankara Üniversitesi'nde profesörlük yaptım. Bu arada da von Humboldt Fellow olarak Karlsruhe Üniversitesi'nde Associate Member olarak ICTP'de bulundum. Ve 2001 yılında yeni kurulmakta olan Koç Üniversitesi Fizik Bölümüne Senior Faculty Member olarak fizik bölümünü ayağa kaldırmak üzere davet edildim ve 20 sene orada hocalık yaptım. Şu anda emeritus öğretim üyesiyim. Emeritusluk emeklilikten farklı bir şey. Yaşar ne yaşamaz statüsü. Hem hocayım hem değilim. Orada adresim oradan, ofisim orada vesaire. Ama yani aynı zamanda da emekli olduğum için yokum yani. Bir şekilde öyle düşünebilirsiniz. Diğerlerini de söylemiyorum. Çalıştığım konular biraz bahsedeceğim. Feza Bey'den bahsetmek için buraya mı yapacağım? Dur, kontrol ediyorum Allah aşkına. Onu görmüyor galiba. Oldu mu? Ha. Well, okay, I will switch to English. And I'm going to talk about Feza Gürsey's biography and his contribution to science in terms of his list of his selected publications. These are not all of his publications, but those are crucial ones that will be, I think, sufficient to show you the depth and the scope of his contributions to physics. As already mentioned, Feza Gürsey graduated from Istanbul University Fen Fakültesi in 1946, and with a state scholarship, he went to London to do PhD at Imperial College, and his first publications, his earliest publications, were part of his PhD thesis done at Imperial College, and he spent 1 more year at University of Cambridge in 1950-1951, and after which he returned back to Turkey. His first paper was Classical Statistical Mechanics of a Rectilinear Assembly. I think Ilmar is going to appreciate that because Young had mentioned this paper and he used it in this derivation of Young-Baxter equation. So this is really, it is amazing how deep intuition he has in physics, and his very first paper concerns what is now called integrable systems and Young-Baxter equations. And his second paper is about on two-component wave equation about Weil spinors, which is 8 years prior to the Weil neutrino hypothesis of Li and Young, which won them the Nobel Prize in 1958 by showing that left-right parity symmetry is violated in weak interactions in weak subnuclear interactions. And he already knew all the mathematics concerning this Weil neutrino problem. And then his thesis, Applications of Quaternions to Field Equations. You might have an access to this, a copy of this thesis. There is a copy at the Feza Gürsey archive, kept at the Feza Gürsey archive at Boğaziçi University. And I want to quote this from James Jean's contribution to Maxwell commemorative volume in 1931. Only the man of science, only the man of science himself ever knows how little freedom he has in choosing his scientific path. One problem leads him inevitably to another, and it may very well be that a man's first scientific research contains within it the germ of a whole life's work. I think this is a good example, his PhD thesis. How many problems, how many new research paths have emerged from this PhD work that's what we are going to see. Now, his second period for publications is from Istanbul University. He started to work there in 1953, and you might notice that he returned to Turkey in 51, and he started at Istanbul University in 1953. He has to do military service, two years, compulsory military service, yedek subay at Ankara, and then he had finished his habilitation thesis during that period, so he doesn't quit physics at all. He had finished his habilitation thesis, and when he returned to Istanbul University in 1953, up till 1957, he published his papers in the Science Journal of the Istanbul University. Now, if you look for this journal now, you won't be able to find it. But on the other hand, when I was a postdoc at Boston, I used to find it at Harvard Library, at MIT Library, and obviously Yale Library has copies, but for only the period 1950s. So this is the sole reason for getting them, for them to get these journals, is to see the contributions of Feza Gürsey. Now, these are all coming dual invariants of Maxwell's tensor. 1995, T-duality is contained in this article. We have studied this in our lectures, part of his lectures, and contribution to the quaternion formulation of special relativity, that's also part of his PhD thesis. Connection between Dirac's equation and a class of spinning particle. This is published abroad because this is the subject of his habilitation thesis. And then correspondence between quaternions and force spinors on some conformally invariant word lines. This is also an amazing paper, which has quite a lot of things to learn, even now, concerning the equivalence principle, for instance. And then his later papers between 57 and 61 are published in journals abroad, but still he is the only author, sole author. Relativistic kinematics of classical spinning particle in spinor form is a repetition, is a continuation of his paper 3. Why it had gone to the end? Am I aim it? Should I aim it here? Bu tarafa gelse daha iyi olacak gibi ama. Bir başa alabilir. Ha. Daha. Biraz daha. Biraz daha. Ha. Okay. Next. Bu tarafa mı yapmam lazım? Ha. Tamam. Now, publication 8 is important. As you have noticed, it concerns Pauli transformations. Now, in the literature, it is called, for physicists, I'm telling this for physicists, it's the gamma 5 translation, or Feza Gürsey'i translation to tell. And it is chirality, concept of chirality is introduced in this paper for the first time. I think this was the first well-known international contribution of Feza Gürsey to physics literature. And then on the symmetries of strong and weak interactions, he has introduced the chiral model, effective quantum field theory, in this paper. And then the well-known nonlinear sigma model paper of Gelman and Levy is published in the same journal, even in the same issue, together with Feza Gürsey. And they are considered as founders of this nonlinear sigma model. And 10 is somewhat unusual because in 1957, in 1956, Turkey and United States had signed a state agreement in the context of Atoms for Peace program. And then Turkey used this opportunity to send its physicists, chemists, and mathematicians to the most prestigious universities in the United States for long periods of time. For instance, Erdal İnönü went to United States and switched to neutron transport theory, taking this opportunity. And Feza Gürsey went to Brookhaven first, and then continued for shorter periods at Columbia, Princeton Institute for Advanced Studies, Berkeley, and before he returned back in 1961. And his first collaborative papers appeared during this period. Now, lepton pairings and then two neutrino theory is something we also, a paper much ahead of its time. It concerns neutrino oscillations between two neutrino types, between electron and muon neutrinos. The tau neutrino is discovered at the end of 1970s. So the problem of neutrino oscillations concerning three neutrino types, which is a very important problem at the moment, is general than this model. But this model, written together with Gerald Feinberg and Abraham Pace, has all the ingredients for discussing neutrino oscillation problem at that early age. And he returned to Middle East Technical University in 1961. Now this period is still, he's publishing papers with a single authorship, very few scientific collaborators. Now the first reference is a review article published in the Proceedings of 1962 Istanbul NATO Summer School. Now this school is something very crucial for the development of theoretical physics in Turkey. Now he invited all his friends, young physicists of the time, which show some promise. And then among the contributors to this conference, I can count Abdus Salam, Nambu, Glashov, Rakah, and many others who have received Nobel Prizes much later on. And when they were very much younger than that, they came and given lectures at Istanbul. And one of the key lectures had been supplied by Feza Gürsey. And I think his contribution to de Sitter spaces and anti-de Sitter spaces is still quoted and used. And the paper on spin 1/2 wave equation in de Sitter spaces, together with T.D. Lee, he is one of the discoverers of wild neutrino problem and the parity violation problem. He is also a Nobel laureate, and he had contributed, they have contributed to this paper on spin 1/2 wave equation in de Sitter space. Now this paper is very important. Reformulation of general relativity in accordance with Mach's principle. This is the very first paper which has the Middle East Technical University as its address. And I joined the TÜBİTAK panel on Monday, and the project proposal concerns Mach's principle and the test of equivalence principle using some quantum techniques. And then I asked the young physicists who's proposing this project, what is Mach's principle? And he said that, well, there are almost 10 different approaches to this question. And I asked, do you know anything about Feza Gürsey's contribution? No. And very surprisingly, also the panel members didn't know anything about Feza Gürsey's contribution. And I think it is physically and mathematically, conceptually, it's a very important paper. I have received a copy of his reprint from Feza Gürsey himself. I was a young student. He tried to explain me the main key concepts, and I don't think I have understood anything at that time. But much later, about 10 years later, I was able to follow and appreciate his deep sense of physical understanding of this problem. And I think I have recommended it to my younger colleagues, and I think it's an important contribution. And also, there are two sets of lecture notes. Spin and unitary spin. This is the SU6 symmetry. Now, this was in collaboration with the Italian physicist Luigi Radicati and the American physicist Abraham Pace. And this is what made Feza Gürsey famous. He became famous for proposing this spin and unitary spin independence, which led to the SU6 symmetry. It doesn't mean anything at this point, SU6, but it is SU3, SU2, etc. But nevertheless, I think Feza Gürsey get most of its citations from this paper, and at one stage, this was considered to be the very promising model, and it is still an important contribution. Now, Introduction to Group Theory is a comprehensive review of Lie groups and its application to symmetries in physics. Now, Lesush Summer School, 1964, is interesting. This is a conference proceedings, and usually conference proceedings used to be published, and you take it and you put it on your shelf till a student needs it, and you hand it down a conference proceeding. Usually conference proceeding books doesn't get published twice and third times. But this is an exception because the lecturers include, besides Feza Gürsey, Dövitt, Lichnerowitz, Penrose, Wheeler, and many such famous people. And it's an interesting collection of papers which gives you the state of science at that period. And Feza Gürsey was invited from Middle East Technical University to contribute this comprehensive review of group theory. And the same thing for the Schladming Winter School in Austria. And this is a comprehensive review of chiral models, which Feza Gürsey was one of the founders. Now, should I comment on this? You see that I have given you in the middle. Formerly, he was a member of the faculty member at the Middle East Technical University, but essentially he was offered a professor position, full-time professor position at Yale University in 1967, and he accepted. And Kemal Kurdaş, the founding president of the university, accepted a double. He accepted that Feza Gürsey should work half-time at Middle East Technical University, spend half his time at Yale, and then whether he should spend some time at Yale or Middle East Technical University, well, he has to choose it, and he has to take students from Turkey, and he has to take students from Yale, and then they have to circulate. But the presidents of the university after Kemal Kurdaş really made him choose an institute, whether he should stay in Turkey full-time or he should stay full-time at the United States. Well, Feza Gürsey spent 1972 and 1973 at Middle East Technical University, taking leave from Yale. And that is when I have taken special relativity, general relativity, and group representation theory. He had given 3 lectures in 2 semesters, and that is the crucial time for me because that is when I learned relativity theory, Einstein's relativity theory, from Feza Gürsey himself, and he has also given a lecture on his own specialty, group representations, and I have the privilege of taking group theory from Feza Gürsey as well. But then afterwards, he had to make a choice, and then he had chosen Yale, and after 1975, he became a full professor at Yale, And then Yale promoted him to Gibbs Professor of Physics, Endowed Chair of Physics, and he was holding this Endowed Chair of Physics, Theoretical Physics, called Gibbs Professor of Physics, which is very prestigious in the States. And then all these prizes followed after that. And his contributions to physics changed a little bit, because during this period, 1991 is when he retired from Yale University. He had taken lots of PhD students, both from Turkey and from the United States and from all over the world. And he had very famous young collaborators. So most of his papers are joint papers. Actually, the first two papers are based on the PhD thesis of Isaac Bars. 4 and 5. These are based on the PhD thesis of Murat Günaydın, and it's the introduction of octonions, application of octonions in strong interaction physics, and they have interesting ideas concerning quark confinement. Lorentz covariant treatment of the Kerr-Schild metric is part of the PhD thesis of my friend Metin Gürses. 7 and 8 are important because this was part of the thesis of his Belgian PhD student, Pierre Skibbe, who was our friend, and a collaborator, Pierre Ramon. These are famous names now. And they have studied as a grand unified theory the exceptional Lie algebras E6 in the first paper and E7 in the second paper. I'm not going to talk about Lie algebras. I'm not going to talk about exceptional Lie algebras, but the construction of the representations of these exceptional Lie algebras made essential use of the octonion algebra. It's an 8-dimensional norm division algebra, which is non-associative. I'm not going to talk about that, but these papers are also well known, and especially the E6 paper is well known. And I think when people are talking about the phenomenological applications of string models, they make essential use of this E6 cut. Now, I heard from Feza Gürsey himself that mathematically speaking, E7 is most exciting and interesting case. However, nature chooses E6. Okay, well, why not? And then another paper concerning complex and quaternionic analysis and chiral and gauge theories. This is also a groundbreaking paper. Chiral theories concern two-dimensional soliton solutions, nonlinear sigma models. Gauge theories concern Young-Mills instanton topological solutions in four-dimensional gauge theories. And complex and quaternionic analysis is a gauge-breaking term paper written together with the Chinese physicist Tize. And the 10th one is potential scattering transfer matrix and group theory. That's the application of Lie group symmetries to nuclear physics. And his collaborator is Isaac Bars, together with Frank Iacchello, who's a famous contributor to this subject. And actually, after Feza Gürsey retired from Yale University, the Gibbs professorship was offered to Frank Iacchello. And this paper is also a groundbreaking paper. I have given you just one example. It's not a single paper, but that's a typical contribution. Now, the next, I have given, these are not all the collaborators, these are not all the papers, but I have given you these 3 papers on purpose, because this is the first time my scientific path had crossed Feza Gürsey's scientific path. Now, if you look at this first paper, octonionic torsion on S7 and compactification of D equals 11 supergravity, published in 1983, and my paper, octonionic geometry and simple supergravity in 11 dimensions, well, almost identical, same year, same journal. Now, we have worked on the same problem, solved the same problem, without knowing each other's work. And then I was invited to give a seminar at Boğaziçi University in 1983, after working out this problem. And at the seminar, Erdal İnönü was there, of course. And next to her, Meral Serdaroğlu, his Feza Gürsey's PhD student, was sitting. And I started to talk about this contribution here. And they told me that, hey, do you know that Feza Gürsey had solved the same problem and published a paper? It was very surprising for me and also very satisfying, because now I'm solving a problem, I'm writing a paper together with my PhD student, and I can work independent of him, and I can publish independent of him the same problem. Now, the other two papers are also very relevant to the work I have done. But as you see, they are later. We get inspiration from this work. But again, if you read self-duality, octonion analysis, the S7, 8 dimensions, etc., and then, our second paper, monopole equations on 8 manifolds with spin 7 holonomy, communications and mathematical physics. We have obtained a set of elliptic system of equations on 8 manifolds with special symmetries, which include the well-known Seiberg-Witten equations in 4 dimensions, which are used for topological classification of the moduli spaces of 4-dimensional Yang-Mills instantons. Now, in 8 dimensions, instanton solutions can be generalized using the algebra of octonions. This is what has been done in this paper here. But the non-trivial set of elliptic system of equations that we call monopole equations, and I think sometime it should be called Bilge-Dereli-Koçak equation, but at the moment it's not very popular, but it is the end result of our interest in this model, and it is published, and it's going to stay there. It's not going to be cited, it's not going to be quoted, but it's there. And the third paper is also, I have memories of that one. This is one of his very last papers. His collaborators at Syracuse University were Balachandran and Kameshwar Vali, and they have considered non-commutative geometry, extension of the standard electroweak theory in using non-commutative geometries and discussing Higgs mechanism. And then we have taken up the same model as an MS thesis with my student at Middle East Technical University. And we have done a renormalization group flow analysis to predict the mass of an observable Higgs boson. There will be extremely heavy Higgs bosons, a number of extremely heavy Higgs bosons, but there will be just one Higgs boson, which will be within the range of observations, possible observations. And in 2000, in MS thesis and later publication, we have predicted a mass 125 to 130 GeV, which we were right on the spot. And well, it was also one thing which is motivated by Feza Gürsey's work, and I think I'm also proud that I have somehow completed one of his last contributions to physics, published in 1991. Now, the main talk I'm going to give concerns supergravity, as I told you. Now, this is the work I have done using what I have learned from Feza Gürsey at Middle East Technical University. I have learned quaternions in lectures on special relativity and general relativity at Middle East Technical University, and I have known about complex quaternion algebra and how they induce local Lorentz transformations in the algebra of complex quaternions. Now, I have applied this to a reformulation of supergravity theory in terms of complex quaternion-valued exterior differential forms over space-time. We have 2 publications here. One of them is a very short one with my long-time collaborator and my close friend Robin Tucker in 1980, a class of exact supergravity solutions, which makes use of this formalism. But the details of the formalism is given in the second paper, worked out about the same time. The details are there, intrinsic analysis of neutrino couplings to gravity, and parts of my habilitation thesis also derives from this work. Now, what we do is the following. The exterior differential forms are coordinate-independent way of expressing laws of gravity in curved spacetimes, and all relevant tensors in this language are free of indices mu and nu. As you know, Einstein field equations are written with indices mu, nu, and everywhere all these indices, and that refer to a chosen coordinate system x mu. Now, if you express everything in terms of exterior differential forms, I'm not going to explain what it is mathematically. You can get rid of these mu-nu indices altogether. You can write mathematically precise expressions, but you don't use any mu-nu indices. It means that you are working out in a way which is free of the choice of coordinates, coordinate-independent way. But still, the theory depends on the local inertial reference frame that you choose. Now, in space-time, a local inertial reference frame means a set of orthonormal 4-unit vectors. They are usually independent of the choice of coordinates at that point. So coordinates and the Lorentz reference frames can be chosen independent of each other. And I'm going to use a different set of indices to refer to coordinates and to local Lorentz frames. So I use A's and B's and C's here. And then the equations that I write should be Lorentz covariant. It should have the same form in every Lorentz under every Lorentz transformation. Now, but we know that complex quaternion algebra carries a representation of spin cover of the local Lorentz group. So you can express everything in terms of mathematically precise expressions which doesn't contain A, B, and C, etc. So this way, by using complex quaternion valued exterior differential over spacetime, you can write tensor expressions which doesn't contain mu's and nu's, which doesn't contain A's and B's. You get precise mathematical expressions, and that's all. Now, I'm going to go through the formal expressions very quickly. Let's not use that. Well, complex quaternion, basis of complex quaternion algebra is, well, of course, one is the basis for real numbers. I is the complex I squares to -1. And then E1, E2, E3 are quaternion units, such that E1 and E2 product is E3 and cyclic permutations of 1, 2, 3. And then they square to -1. Now, these are not something mysterious. Actually, when you do quantum mechanics and when you deal with spin in quantum mechanics, you use Pauli spin matrices, 2x2 matrices. Well, 2x2 matrices are precisely those quaternion units. And spinors that I'm going to talk about are the spin states of the electron, spin up, spin down. And nowadays, quantum computation people call them qubits, 0 and 1, spin up, spin down. These are not something mysterious, but if you want to do complex quaternion, you extend the quaternion algebra generated by 1 and 3 quaternion units by I, and then I times Z1, I times Z2, I times Z3. And then the rest follows. I'm not going to go into any detail. This is a non-commutative algebra. And I introduce a Lorentz frame, coframe, in this way. It's a complex quaternion, I times E0, that's a pure imaginary one form, and this is a quaternion valued one form, 1, 2, 3, sum on 1, 2, 3. Now, I have lots of conjugations here. I can get complex conjugation. Complex conjugation takes I to -I. I can get quaternion conjugation. Quaternion conjugation takes a quaternion unit to minus itself, and I can do this one after the other, and that's Hermitian conjugation. And then we have three different conjugations. Star to the right of a symbol denotes complex conjugation, which takes minus here. A bar over a symbol means quaternion conjugation. E bar means the second term has a minus here. And then if you do this together, one after the other, you get minus, minus. So it is the Hermitian conjugate. It's an anti-Hermitian basis, one form. And then all the geometry can be given in terms of that. Lorentz invariant. Oh. Çok hızlı gideceğim ama hop. Okay. Metric tensor is given. Its Lorentz transformation is given in terms of a unit quaternion. Q bar Q or Q bar is just identity. And then I have defined a complex quaternion valued connection one form, torsion tensor, curvature tensor, no indices as you see, no mu indices, no AB indices. If anybody is interested, I can give you the details. The Bianchi identities, Lorentz transformation properties of these basic tensors, T and R, and the connection transformation here without any indices. And now comes up. Evet. Burada bir sorun oluyor mu? Oldu mu? Okay. A Y spinor transforms from the left. Exterior covariant derivative is given. A conjugate spinor is defined that way. What's a conjugate spinor? Dotted spinor, undotted spinor. It's not so difficult. Dirac operator is a 4x4 matrix, linear differential matrix operator. A 4x4 matrix operates to the right on a column matrix. It's an undotted spinor. But I know that the conjugate of this 4x4 Dirac operator is a 4x4 matrix. It can also operate to the left on a row matrix. That's the conjugate spinor. So that is what is called the dotted spinor. So we have a column matrix, the Dirac spinor or a wide spinor, which is an undotted spinor. That's what I have here upstairs. And then the conjugate is a dotted spinor, which is a row matrix. This is the simple case to understand. And then Y spinors can be represented by, in the algebra of complex quaternions, by left ideals generated by these L1 and L2 sets, or right ideals. And I have given them explicitly in terms of quaternion, complex quaternion units. Now, this is again something not so mysterious. Why? Because if you have a 4x4 matrix, it's a general Clifford algebra element. Now, a 4x4 matrix can be decomposed into its column matrices, 4 of them, or you can decompose it into its row matrices. Now, column matrices are left ideals, row matrices are right ideals. So, in order to project out a 4 spinor from a Clifford algebra element, you apply to the right by a minimal left ideal, these operators. And really, in order to define spinors and conjugate spinors, one of them transforms under Lorentz transformation by action to the right, and the conjugate spinors transform under Lorentz transformations by the Q-dagger action from the left. And then you can define spin treehouse fields, which have to be Majorana. This is technical. I'm not going to go into any details here, but let me just give you this expression here. You see that this is a precise expression, mathematically precise expression. There is no index involved, but the order of these elements, entries are important because complex quaternion is a non-commutative algebra, so you cannot change the order of these objects at will. And also there are lots of... Almost that. I'm almost finished. Okay. And then I have complex conjugation, I have quaternion conjugation, I have undotted spinors, dotted spinors, etc. Now, variation of these expression is horrendous. It doesn't carry any indices, but it is still very difficult. And you can simplify the variational field equations, and you can get Einstein equations coupled to spin treehouse Rarita-Schwinger field equations subject to the space-time torsion given in terms of gravitino vector spinor field by a quadratic term. Now, that is the supergravity field equations without any indices. It's mathematically precise, simplified, and we looked for solutions of these supergravity field equations. Now, I think I'm not going to give you any details or any explanation about why colliding waves. Sonra cevap vereyim. Hop, yine takıldık. Aha, colliding waves. Colliding wave ansatz. Maybe you can check my... Ne oldu gene? Hop. Buraya mı yapmam lazım? Ne oldu gene? Hop. Bir sayfa daha var. Bir sayfa daha var. Öncekine mi istiyorsunuz? Bundan sonra bir sayfa var. Son sayfa. Son sayfa. Ha, that's it. Well, in fact, these are my latest publications with a collaborator of mine, Yorgo Şedikoğlu. He was a postdoc, but later on we started to collaborate. Now, you see that simple supergravity PP waves, that's the problem that I worked at Vienna, 1978. And then, for some reason, I haven't done this solution, given this solution in terms of complex quaternions. Now, my postdoc expressed interest in learning complex quaternionic formulation, so we had went back to my old work 44 years ago, and then rederived all these expressions, the solution, and we published in 2022. There is a gap of 42 years in between. And then we applied it to an important problem which had been not solved for 40 years. And again, that's surprising, because I could have solved this problem in 1982, but I haven't bothered, because I knew everything about colliding gravitational waves, because my friends at METÜ are working on that. We had been discussing them with Yavuz Mutlu, Rahmi Güven, Mustafa Halil all the time. I knew everything about colliding gravitational waves. I worked out supergravity plane waves, and for some reason I didn't let them collide. And then we had solved this colliding supergravity plane wave solutions last year. It's published in the same. But in order to understand this solution, you have to understand this notation of complex quaternionic valued differential forms. The reason for that is, the reason why this problem had not been solved before is because when you choose your metric, the coordinate frames, you have to choose your spinor ansatz. Up to that point, everything is fine. But then, in the usual formulation, you need a set of gamma matrices. And the choice of your gamma matrices is up to you. And then if you choose a suitable coordinate system, null coordinate system for expressing your colliding wave solution, in order to work out everything in the collision region, you have to invent a convenient set of gamma matrices which blends in well with the choice of your coordinates. This is impossible, next to impossible. You have to do a lot of guesswork, and this problem is not solved for 40 years. But with this formalism, inspired by Feza Gürsey's work on quaternions, we don't need gamma matrices at all, because once you choose your quaternion basis, that fixes your spin basis. And then if you change your forms to null forms, your spin base also changes accordingly. And then you can work out these terrible equations in distribution sense, and we can give solutions. In the collision of gravitational waves, the problem is there is a plane wave coming this way. There is another plane wave coming this way. Empty space-time in between. They hit each other. Their faces, plane fronts are parallel planes. When they pass through each other, Einstein equations are essentially very nonlinear. So when they collide and pass at the back, you get something very nonlinear, very complicated looking expressions. It's very difficult to solve exact solutions there. But for pure gravitational wave collision, at the end, at the back of the collision of two plane waves, we have a line curvature singularity created. So collision of pure gravitational waves, impulsive waves, create essential singularities at the back. Now this way, we cannot find it with supergravity. We have found collision of gravitino waves, and in some sense, the graviton sector or the metric sector is inert, and a curvature singularity doesn't develop. And it was an interesting piece of work. There is still work to be done because colliding supergravity plane waves, spin treehouse coupled to gravity is solved. But you might think that massless spin 1/2 neutrinos coupled to gravity should be easier. But mathematically, it turns out to be a lot more complicated than this case. So we still have some open problem left. Well, I hope I can continue with this problem. This problem is totally inspired by Feza Gürsey's knowledge of quaternions, complex quaternions, their representations of the Lorentz group induced by quaternions. And when I went to Lancaster, I knew them already. I didn't have to learn them there. It was interesting because when I went so maybe I should say something about METÜ. When I went to my postdoc positions in Vienna, in England, in Germany, people thought that, well, maybe you have learned exterior differential forms from Tiring. He's the director of the Institute for Theoretical Physics at Vienna, a famous physicist with books written in this language. And people thought that since you were in Vienna, you must have learned exterior differential forms from Tiring. But that's not true because I learned it in Middle East Technical University from Turkish physicists, from my friends and Yavuz Nutku. And also, when I worked out this formalism in Lancaster University, people obviously assumed that I learned at Lancaster. But on the other hand, I was a student of Feza Gürsey, and when I went to Lancaster, I already knew all these expressions and all the mathematical formalism. I heard this statement many times. Türkiye'de doktora yapılmaz. I heard it from lots of foreign professors from the United States, from Europe. I used to argue with them. Why shouldn't I do theoretical physics in Turkey? Of course, I'm going to do first-rate theoretical physics in Turkey. I should be doing that. Okay, that's fine. I can defend myself. But on the other hand, when I hear that from students in Turkey, from my colleagues in Turkey, Türkiye'de doktora yapılmaz, I don't know what to say. Burada bırakayım isterseniz. Peki. Teşekkür ederim. Buraya geliyorum herhalde.
Efendim,
uzattın mı?
Kıymetli hocam, Profesör Doktor Tekin Dereli'ye çok teşekkür ediyoruz. Ben görüyorum birkaç soru olduğunu görüyorum ama programımın akışına devam etmem gerekiyor. En sonunda toplu olarak sorularınızı sizlerden rica edeceğiz. Ve ben şimdi... O da olur. Peki nasıl isterseniz hocam? Burak Beyciğim mikrofonu iletelim hemen arkadaşımıza. Sorunuzu alalım. İkinci bölümde bildiğiniz gibi online olarak video konferans yöntemiyle uluslararası misafirlerimizle bağlantı kuracağız. O yüzden ben de zamanı doğru kurgulamaya gayret ediyorum. Çok teşekkür ederim. Buyurun.
You're welcome. Thank you for your presentation. This is Mutluhan. I'm from OSTİM Technical University and University College London. Since I'm coming from education background, I just wondering that as I see, Feza Gürsey has written almost all of his papers alone by himself. Yeah, exactly. That's correct. And I'm wondering that, is it something or is it a sign of showing that Feza Gürsey was beyond the time he lived? Or is it something that makes Feza Gürsey different from the
well, he has his own style,
colleagues?
Of course, he has his own style. And the problems he is interested in is much ahead of his time. And he has a very deep insight. And I don't think you have realized how important his problems, his papers had become in time. At the time, it wasn't appreciated much by other people. I think he was ahead of his time. He has a very deep insight into physics, where it is going. And it's amazing. I think in some way, he knew where the physics is heading to.
Yeah, I got it. Then we can say that Feza Gürsey was so keen in doing something new or concept in physics at the time.
Well, he has a very deep knowledge in physics. Great. I think I haven't said this, but when he was teaching us, there were lots of controversies and discussions at Middle East Technical University about what's theoretical physics, what's experimental physics, and then we have two different camps. There are experimental physicists and there are theoretical physicists.
Yeah.
But on the other hand, we were discussing, I have my friend
so
here,
exactly.
An experimental physicist. I have taken 11 experimental physics courses in my student days. I was very good at it, but I chose to do mathematical physics. And Feza Gürsey used to always emphasize that you should do physics by emphasizing the physical applications and experiments. You should always quote experiments. And that's the habit that we got from him.
Oh, okay, thank you. And lastly, I'm sending my greetings to Feza Gürsey and others in front of you. Thanks.
Evet, çok... Peki başka sorumuz sanırım yok şu an. Tamam, çok teşekkür ederiz. Çok sağ olun. Efendim şimdi de New Haven, Yale Üniversitesi ve Gürseyler ile hoş anılar konu başlığı için Sayın Rektörüm Profesör Doktor Murat Yüle'yi sahneye de kürsüye arz etmek istiyorum hocam.
Evet, tekrar merhaba. Benim söyleyeceğim şeyler hocam gibi teorik fizikle alakasız. Ben makine mühendisliği okudum Boğaziçi'nde. Ama hiç hayatta mühendislik yapmadım hocam. Annem fizikçi olduğu için biraz fiziği seviyordum ama mühendislik tarafını okuyup hiç yapmamış birisiyim. Benim konum bugün Gürsey ailesi ile olan hatıralarım. Birazdan da İskender Öksüz Hoca, o da Yale'de kimya doktorası yapmış bir hocamız. Siz tanırsınız belki. Evet, o da katılacak. O da daha çok herhalde anılarıyla şey yapacak. Şimdi bir hazırlığım da yok. Her şey doğaçlama. Yalnız küçük bir sunum var. Onu koyabilirsek. Şimdi de sizi dinlerken birisi bir şey göndermiş. Sizden teorik fiziği bu kadar dinledikten sonra onu da koyalım istedim ama bilmiyorum, vakit koydunuz mu? Ona en sona bir alalım o zaman. Hocam sizin bu kuantoryumlar, vektör algebrası vesaire. Şimdi ben onun size Karadenizli mühendislik tarafını göstereyim. Mekanik, pratik koyabilecek miyiz en son sayfaya? Hocam bakın. So our guest from Korea, I think I had to translate it to you. This is a funny message that came to me while I was listening to our professor. So this is an invention, modern invention for capturing mosquitoes. So he says, the inventor says, in the first step, the mosquito dives into the white powder, thinking it's sugar, because mosquitoes love sugar, but actually it's salt. So he gets frustrated. Then he goes into the bottle cap, which has raki inside, not water, but raki. So after salt, he wants to drink water from the water cap, bottle cap, but it is raki, so it gets drunk. And then while it's walking, it tumbles into the wooden bar. It falls on the stone. It gets fainted, and then it dies. So this is an invention. Maybe we can file an invention form for it. But of course, all the lectures and all the life of Professor Feza Gürsey was into much deeper subatomic level physics, and he was a leader. He was ahead of his time. So my experience with them, Türkçe devam edeceğim. Yale Üniversitesi'ne üçüncü yüksek lisansımı yapmak için 92 yılında gittim. Yale Üniversitesi'ni seçmemin sebebi de tarihçesiydi, köklülüğüydü vesaire. Esasında doktora programındaydım Bilkent'te. O doktora programında doktora tez araştırması için Sidney Afriyat, bizim iktisat alanında mikrocu bir hocamız var. Çok tanınmış bir hoca. By the way, you can follow these through our translating software. So he helped me apply to two colleges, one in Cambridge, one in Oxford. I got accepted from both because I had a very strong reference. But then I selected Yale because there it was going to be both a research and at the same time a master's degree, third master's degree. So I went into the master's, the Graduate School of Management. So this is one picture. I was the student marshal. They call it a student marshal. So I was the, let's say, representative of the graduates of that year. So this is our, from that one. Geçelim onu. Bende mi şey? Bu çalışmıyor. Yale Üniversitesi İşletme Bölümünden yüksek lisans derecesi almak için öğrenci olarak gittik. Gitmeden evvel tabii Yale hakkında hiçbir şey bilmiyoruz. Tesadüfi olarak biraz evvel ismi geçen Feza Bey'in oğlu ve Süha Hanım'ın oğlu Doktor Yusuf Gürsey. O da fizikçiydi. Brown'dan fizik doktorası. Çünkü bütün aile fizikçi. Yani Feza Hanım da fizikçi. Feza Bey fizikçi, Süha Hanım fizikçi. Oğulları da fizikçi. Ama oğlu hakikaten çılgın bir fizikçiydi. Onunla olan anıları da anlatacağım. Rahmetli. Tesadüfen Amerika'ya gitmeden hayatta ilk defa Amerika'ya gidecektim. Geliniyle, yani Yusuf'un eşiyle benim eşim tanışmış Ankara'da. Tesadüf. O sırada Süha Hanım da Ankara'daymış. Sağ olsunlar, çevre sokakta bir evleri vardı. Belki bilirsiniz. Biz onları bir çaya davet ettik. Çünkü annem de ODTÜ Fizik bölümünün ilk asistanlarından. İlk kurulduğu zamanki asistanlarından Süha Hanım, Feza Bey, tabii Erdal İnönü asıl. Onların öğrencisi 2-3 sene kadar asistanlık yapmış diye hatırlıyorum. Şimdi o da bizi dinliyor, muhtemelen katılacak. Süha Hanım'la ilk defa orada tanıştık. Feza Bey o zaman vefat etmişti. Ben Feza Bey'i hiç yüz yüze görmedim. Sadece ismini Bilim ve Teknik dergisinden öyle büyük insan olarak öğrenciliğimizde görüyorduk. Tabii Süha Hanım'ı görünce ben hem çok sevdim hem çok hayran oldum. Çünkü gerçekten bir saray hanımefendisiydi Süha Hanım. Birazdan resmini göreceksiniz. Üniversiteye gittiğimiz zaman tabii Yale Üniversitesi belki biliyorsunuz Amerika'da bu ilk üniversiteler William and Mary College, Virginia'da, arkasından Harvard, arkasından Harvard'daki hocalar, biraz hocaların arasında da bazen problemler çıkıyor ya, öyle bir kavga ediyorlar. Yale ayrılıyor bir grup, Boston'dan aşağı iniyorlar, New Haven'da Yale Üniversitesi'ni kuruyorlar. Yale Üniversitesi'nin amblemi, geri gelirsek, İbranice, yani ikinci İncil. Onlar öyle diyorlar. Old Testament, New Testament. Bu birinci İncil'den daha doğrusu. Bu modern tabii de asıl Yale'in ambleminde 3 tane İbranice harf vardır. Amerika'daki bütün okullar Hristiyan, oraya gelen ilk çok inanmış Hristiyanların kurduğu kilise okullarıdır. Harvard da öyledir, Yale de öyledir. Yale'den kavga edip ayrılanlar da, kavga demeyelim de işte görüş ayrılığı diyelim, onlar da Princeton'ı kuruyorlar. Biraz daha aşağı iniyorlar. Tabii Yale, Harvard kendisini böyle eski okullar olarak falan görüyor ama William and Mary ilk kurulan okul, 1639 falan olması lazım. Onlar da bunlarla dalga geçmek için şey derlerdi, işte sizin gibi bu yeni genç okullar falan. Çünkü Yale'in kuruluşu galiba 1700'lü yıllar. Neyse, New Haven, Charles Dickens'ın da hikayelerinde geçen, Amerika'ya ilk doğu kıyısına göç eden Püritanların kurduğu kasabalardan bir tanesi. Boston'u da onlar kurmuşlar. Tabii orada bizim kuzenlerimiz olan Kızılderililer dedi biraz evvel hoca. Kızılderili dediğimiz şey esasında Asya'dan işte eksi 30 binlerde falan göç eden bizim Asyatik insanlar. Yani bizim kuzenlerimiz. Ama ondan sonra bu Puritanlar geliyorlar, New Haven'ı, Boston'u vesaire kuruyorlar. New Haven güzel bir kasaba. Fakat benim oraya gittiğim yıllar 92 yılıydı. Çok büyük problem vardı. Çünkü iktisat bölümünün önünde bir doktora öğrencisi akşam saatlerinde bıçaklanarak öldürülüyor. Öyle olunca Yale'in sıralamaları aşağı iniyor. İşte beşinciliğe düşüyor bilmem ne falan. Öyle zor bir dönemdi. Bunun sebebi de 1982 Amerika'da bir resesyon yaşanıyor. O resesyondan sonra buralar ilk sanayileşen yerler olduğu için ilk sanayileşen yerler, resesyonda da ilk kurulan yerler, çok büyük bir işsizlik var. İşsizlik olunca suç da yükseliyor. Mesela Hartford, Connecticut'ın başkenti, suç oranları çok çok yüksek. New Haven'da yüksek. Böyle olunca tabii öğrenci kalitesi düşüyor vesaire. Biz bunları o kadar bilmiyoruz ama gittiğimiz zaman üniversite tarafından bize verilen ilk oryantasyon hayatta kalma oryantasyonuydu. Yani sokakta birisi önünüzü keser de sizi bıçaklamaya kalkarsa ona nasıl çok kibar davranıp istediği ücreti güzelce verip hayatınızı nasıl kurtaracaksınız? Asla karşı koymayacaksınız. Asla kendinizi akıllı sanıp cebinizde sıfır parayla dolaşmayacaksınız. Çünkü ona da kızıyorlar. Bunlar hep o eğitimden kalan, aklımda kalan şeyler 35 sene önceki. Yanınızda mutlaka bir 10 dolar hemen vereceksiniz. Kendinizi akıllı sanmayıp parasız dolaşmayacaksınız. En az 10 dolar veya 20 dolar yanınızda olacak. Önünüzü kestiği zaman arkadaş güzelce çıkartıp kibarca kendisine vereceksiniz, teşekkür edeceksiniz. Hayatınızı kurtarmış olacaksınız. Biz tabii ilk gün gittik, bunları o kadar bilmiyoruz. Havaalanından bu bizim havaşlar gibi şeyler var. Onunla New Haven'a geldik eşimle. Yeni evliyim. İndik. Ya taksiyle ya da bizi Yusuf aldı. Yusuf aldı galiba. İlk akşam yemeğimize akşam saatlerinde indik zaten. Süha Hanım'ın yaptığı York Street, 100 York Street. Orayı görmüşsünüzdür. Medical School'un orada. İşte orada sağ olsun Süha Hanım bize bir yemekle karşıladı. Yemeğimizi yedik. Karşı tarafta da öbür binada bize bir yer tutmuşlardı onlar. Oraya geçmeden Yusuf aldı galiba. Yusuf'un yanında İbrahim Semiz vardı. Hatırlar mısınız? Fizikçi. Bizim Boğaziçi'nden bizden 2-3 sene önce mezun olmuştu. Bu toplantıya da katılacaktı galiba ama katılmadı herhalde. Şimdi hiç unutamadığım şey şu. Yusuf'la İbrahim uzay yolu izliyorlar. Star Trek. Şimdi biz de uzay yolu izlerdik. O biliyorsunuz birkaç jenerasyon olmuştu. Fakat biz uzay yolu izlerken film izler gibi izlerdik. Yani Cüneyt Arkın'ı nasıl izliyoruz? Uzay yolunu da öyle izliyorduk. İbrahim Semiz'le Yusuf izliyorlar ve fizik yorumu yapıyorlar. Yani dedim bu nasıl bir şeydir? Gerçekten hiç unutamadığım bir şey. Şimdi o zaman şimdiki gibi DVD, işte IPTV falan da yok. Durduramıyorlar da. Bir sahne görüyorlar, onu subatomik fizik açısından yorumluyorlar. Ben hiçbir şey anlamıyorum tabii. Dedim ya bu arkadaşlar hangi gezegenden geliyor, bunlar nedir, nasıl insanlardır falan. Sonra tabii Yusuf'u tanıyınca gördük çok aşırı zeki. Yani aşırı zeki bir insandı. Allah rahmet eylesin. Bazı hatıralar söyleyeceğim dedim. Mesela annesine hiç anne dememiş. Babasına da hiç baba dememiş. Doğduğundan beri, konuşmaya başladığından beri. Annenin adı Süha, babanın adı Feza. Anne ve baba kelimeleri şeyinde yok. Yanlış hatırlamıyorsam Yusuf Gürsey bir fizikçi, yani bir zeki bir fizikçi. Sadece bir tek renk pantolonu vardı hocam. Gri. Gri pantolonları vardı. Şimdi onu niye yapıyorsun? Ya her gün sabah kalkıp hangi renk, ne pantolon giyeceğime niye karar vereyim? Kafamı niye yorayım? Gri pantolon, her gün sabah o pantolon. Bir de galiba ceketi vardı. Böyle bir enteresan bir insandı. Ama hakikaten insandı yani. Gerçekten insandı. Süha Hanım gerçek bir saray hanımefendisiydi. Gerçekten öyleydi. Bir resmini bir sonraki şeye alalım. Süha Hanım'ın bunu 2004'te oraya bir konuşma için gittiğimde Yale'de çekmişim. 27 Mart 2004. Tabii biraz çökmüş zamanları ama yüzündeki nuru görüyorsunuz, enerjiyi görüyorsunuz. Şimdi bir daha gelelim, biraz daha gençliği, 10 sene öncesi var bir yerlerde galiba. Bu aynı, devam et. Benim o konuşma için gittiğim zaman geriye gelelim, biraz daha geriye. Bir sonraki, yavaş, bir daha, bir sonraki. Bunu birkaç ev değiştirdik tabii 90'lı yıllardan beri. Bize gönderdiği bir şeymiş. Yaş günü müydü? Mezuniyetten. Çeyrek asırlık bir Gürsey annesinin devamı uğruna sana layık olmayan bu kalemi takdir ediyorum. Ne yazıyor orada? Feza, bu kalemin mütevazi bir modeliymiş. Feza'nın imiş. Hayatı feza füze gibi zevkle atılacak inşallah. Süha. Öbür tarafta da bir başka not var. Onu da öyle biraz amatörce yapmışız bunları tabii. Çeviremeyiz. Feza Hanım gerçekten böyle bir hanımefendiydi. 2 sene boyunca biz öğrencilik dönemimizde Yemeklerimizi onda yedik. Televizyonlarımızı onda seyrettik. Eşimin üniversite başvurusu, transferi daha doğrusu sağ olsun. Onun sayesinde gidip Albertus Magnus College diye bir şey vardı. Onun sayesinde oldu. Bir de devam edelim. Bütün her şeyi koymamışsınız galiba. Bitti mi burada? Birçok şeyi koymamışsınız. Sasnovlar vardı. Tabii şimdi ilk baştaki evleriniz, siz belki onu biliyorsunuz, bahçeli evleri. Biz oraya gittiğimizde Feza Bey vefat etmişti. Ondan önce mi sonra mı bir apartman dairesine taşındılar. 100 York Street, o bina hala duruyor. O 100 York Street'te önceki evleri de öyleydi ama sonraki evleri de Türkiye'den gelen Meral Serdaroğlu dahil, Aysıt Tansel dahil ne kadar doktor öğrencisi veya araştırmacısı varsa bir dergah gibi, bir tekke gibi bunların evlerinde o öğrenciler hep kalırlarmış. Süha Hanım onu çok anlatırdı. Feza Bey makalelerini o insanlarla beraber olmaktan çok hoşlanırdı dedi. İşte mesela çay içiyoruz, pasta yiyoruz, yemek yiyoruz. O genç öğrenciler, onların evleri, yurtları falan az olduğu için hep bunların evlerinde. Feza Bey de onlarla beraber olmaktan çok hoşlanıyor ama bu arada kafasında bir paper var. Onlarla konuşurken bir taraftan paperları yazarmış. Tabii o zaman laptop da belki yoktu. Elle mi yazıyor, ne yapıyorsa. Yani o bir taraftan onlarla konuşurken, hoşbeş ederken bir enerji oluşuyor tabii. Bir taraftan o teorik fizik makalesi yazarmış. Bunu hiç unutmuyorum. Geçmişten çok bahsediyordu Süha Hanım. Bazı tanınmış isimler var. Onlar da bende kalmasın. Sizde de varsa siz de hocam anlatırsınız. Bülent Ecevit'ten çok bahsediyordu. Bülent Ecevit rahmetli başbakanımız Londra'da kültür ateşesi olarak çalışırken Feza Hoca da Imperial College'da doktora yapıyormuş. Bu ikisi de aynı yaşlarda herhalde arkadaşlar. Derdi ki Bülent bazen şiir yazmaya çalışırdı. Yazardı değil, yazmaya çalışırdı. Allah rahmet eylesin. Yani pek de yazamazdı diyordu. Yani Bülent'in şiir yazma kabiliyeti pek yoktu diyordu. Ya da bunu hissettiriyordu. Şimdi ikisi de ölmüş, şey yapmayalım. Ama Feza Bey'in edebiyat tarafında korkunç bir şeyi var. Bir kazanımı varmış. Ben mesela kütüphanesine baktığım zaman büyük kütüphanesi kalmamıştı orada ama ya içinde neler vardı? Farsça sözlük, Kürtçe sözlük, bilmem ne edebiyat şeyi var. Ben şaşırmıştım. Yani bir fizikçinin niye böyle bir şeyi var diye. Getirip gösteriyormuş. Ben şiir yazdım, bir bakar mısın, değerlendirir misin diye. Şimdi Feza Bey de herhalde doğrucu bir insan. Hani çok güzel yazdın da diyemiyor, harika da diyemiyor. Diyormuş ki Bülent'ciğim biraz daha şuralarına bir baksan diye geri gönderiyormuş. Bülent Ecevit de tabii nazik ve kibar bir insan. Bozulmuyormuş ama kendine de güvenli olduğu için tamam diyormuş, gidiyormuş. Bir de şeyden bahsetmişti. Hurşit Güneş Hoca var. Hurşit Güneş'in babası eski bakanlarımızdan. Efendim? Turan Güneş. Şimdi ondan bahsetmişti bir defasında. Gelip anlatmış bunu Feza Hoca'ya ve Süha Hanım'a. Bu tabii yerinde duramamış, siyasete girmiş akademisyenlikten. Onlar da galiba Trakyalı bir aile. Hurşit Hoca'yı ben tanıyorum da şimdi nereli olduğunu çıkartamıyorum. Siyasete atılmış. Tabii siyasete atılınca gidip halka bir şeyler söyleyeceksiniz. Kuantum mekaniği falan anlatamazsınız. Oy isteyeceksiniz. Diyormuş ki 1960'lı yıllar galiba, diyormuş ki her gittiği kahvede kahve konuşması yapıyor. Sizleri ey halkımız, sizleri bilinçlendireceğiz. O sırada herhalde o bilinçlendirme lafı yeni çıktı muhtemelen. Öbür kahveye gidiyor. Ey halkım, sizleri bilinçlendireceğiz. Bir tarafa daha gidiyor. Ey halkım. Halk da esniyor. Şu anda bazı gençlerimizin olduğu gibi. Diyor ki yanına hangi parti bilmiyorum, CHP galiba. İl başkanı geliyor, diyor ki kulağına eğiliyor. Beyim bir dakika diyor kulağına. Beyim diyor, bak insanları uyutuyorsun. Bunun sebebi diyor, bizim burada diyor piliç olmaz diyor. Bizim burada büyükbaş hayvancılık vardır diyor. Piliçten bahsetme insanlara diyor. Bu da herhalde tarihin derinliklerine gidecek bir şey ama bana Süha Hanım anlatmıştı. Burada resim çıkmamış. Şöyle birkaç hadise oldu. Onları da anlatıp ben ayrılayım. 92 yılında biliyorsunuz Bosna katliamları oldu. Şu anda Gazze'de olduğu gibi o zaman da Bosna'da Sırp Çetniklerin katliamları vardı. Biz Amerika'ya Ağustos ayı gibi gittik. O zaman iyice artmıştı. Ve kendi olduğumuz okulda, yani School of Management'ta bu katliamlara karşı ne yapabiliriz falan diye işte bir şeyler yapmaya çalışıyoruz. Ne yapalım? George Kenny isimli Amerika Dışişleri Bakanlığı'nda çalışan Bosna'dan sorumlu Amerikalı birisi o sıradaki Amerikan hükümetinin Bosna'daki inaction'ını, yani hareketsizliğini, bir şey yapmayışını protesto etmek için istifa etti. Şimdi Amerika'da bir dışişleri görevlisinin Amerika'nın Sırpların Boşnakları katliama tabi tutmasından dolayı görevinden istifa etmesi çok büyük bir olay. Çünkü bu adam bir kere evine nasıl ekmek götürecek? Yani adam Dışişleri Bakanlığı'nda çalışıyor. Wall Street'te çalışmıyor, başka yerde çalışmıyor falan. Biz de bu kişiyi Yale'e davet ettik. İşte orada konuşma yaptırdık. Öyle şey oldu. Süha Hanım da ona geldi. Sonrası tabii Süha Hanımların çevresi çok genişti. Bir Yahudi aile orada bir organizasyon yapmış ve dediler ki işte biz burada Amerika New Haven'daki halk olarak Bosna'dan bu katliama uğrayan ailelerden buraya getirebilir miyiz? İşte biz onu bir ev bulalım, bir şey yapalım, yardımcı olalım, kurtaralım Sırplardan diye. Tamam. Ondan sonra biz de işte iki genç olarak o şeyin içine katıldık. İşte Boşnaklar geldiler. Tabii Amerika'ya gelince Boşnak aileler çok takdir edersiniz katliamdan kurtulmuşlar, oraya gelmişler ama orada o grubun içinde Türkleri görünce çok rahatladılar. Yani öyle bir güven geldi, rahatladılar ki ilk başta geldiklerinde böyle korkulu, bizi burada yiyecekler mi, içecekler mi falan diye bakarken bizleri görünce tabii Türkleri kendilerine çok yakın hissediyorlar, şey yaptılar falan. Sonra o gruptan resmi gösteremedik. Yine bir Yahudi bir aile, Barry'di galiba adamın ismi, Sasno. S-A-S-S-N-O-W. Bu ailenin, bunlar New Haven'lı bir aile, karı koca, yaşlılar, çok geç yaşta çocukları olmuş. Çocukları Yale'i bitirdikten sonra Princeton'da iktisat doktorasına kabul edilmiş. Fakat o da trajik bir kaza, doktorasını tamamlayamadan çocukcağız ölmüş. Ölünce bu aile, anne baba, tek çocukları var. Yale'e Princeton'a bir şey vermişler. Orada işte grant deniyor. Kütüphanede bir şey açtırmışlar. Onlar da oraya o ailenin ismini yazmışlar. Dediler ki ben de orada bir taraftan iktisat, bir taraftan işletmedeyim. Ya acaba Murat, Süha Hanım'a söylemişler. Murat bizimle gelir mi? Bu seneki hatıra şeyine, Yale'deki Princeton'daki dekan, ki o da çok meşhur birisiydi bizim finans alanında, Burton Malkiel diye bir hoca. Random Walk Down the Wall Street diye çok meşhur bir kitabı vardı, finansçı. Bizimle gelip işte törene katılır mı? Biz de Süha Hanım'ı aldık. O sırada anne babam da oradaydı. İşte Princeton'a gittik. Dekan bize tabii Princeton'da bir işletme dekanının misafiri olmak falan öyle önemli şeyler. O zaman biz öğrenciyiz. İşte bizi bir yemekte yaptı. Anne babası orada. Biz oradayız. Ondan sonra o şeyin altında bize bir şey yaptılar. Süha Hanım da katıldı. Bunu da şundan yaptım. Yani Süha Hanımların gerçekten çok geniş bir çevreleri vardı. Her türlü şeyden, Türk'ü, işte Yahudisi, Amerikalısı vesaire. Çünkü çok gönlü bol insanlardı. Bize 2 yıl boyunca annelik yaptı Süha Hanım. Ve tabii Yusuf da. Son şey de şu hocam, sizin bu şeylerinizi dinledim. Çoğunu pek bir şey anlayamadım açıkçası. Çünkü matematiğini de unutmuş. Ama anladığım kadarıyla bizim lineer cebir dediğimiz şeyin biraz daha gelişmişi gibi bir şey değil mi? Vektör algebra gibi bir şey. Şimdi bana o şunu hatırlattı. Burada geçen sene miydi, ondan önceki sene mi biz bir başka anma yaptık. Anma, Rasim Özdenören, bir Türk yazarı, benim de tanıdığım, hikayeci ve düşünür. Ona da bir anma yaptık. O da bizim bir değerimiz. O anmada ben şunu anlatmıştım. Şimdi sizin dediğiniz anlattığınız şeyler ben de onu çağrıştırdı. Boğaziçi Üniversitesi dereceyle üniversiteyi kazanmışız. Annemin yönlendirmesiyle son sene ODTÜ makineden tercihimi Boğaziçi makineye çevirmişim. Çünkü Boğaziçi'ni annem bana bir gel de bir gör demiş. Ben Boğaziçi'ni görünce demişim bu ODTÜ'nün beton binalarından yani burası çok daha güzel. Boğaziçi'ne gitmişim. Matematikte falan iyiyim. 1. sınıfta Rasim Özdenören'in bir kitabını okudum. Adam hem edebiyatçı hem düşünür. Ben de o sırada babamın da yönlendirmesiyle klasikleri okumaya çalışıyorum. İşte Dostoyevski okuyorum, bilmem ne okuyorum falan. Niye okuyorum? Ya işte bunlar büyük adamlar, bunları okumak lazım. Edebiyat da önemli bir şeydir falan. Fakat aklıma şu geliyor hep. Ya bu edebiyat ne işe yarar? Yani insanlar niye edebiyat yaparlar hocam? İnsanlar niye fizik yaparlar? Mesela Van Gogh niye hayatını resim çizerek geçirmiş? İnsan anlaşılmaz bir şey. Şimdi bize çok saçma geliyor. Mesela çok değerli bir şeydir ama Van Gogh niye bütün hayatını resim çizerek geçirmiş? Kardeşim fizik yapmak varken. Ama bazı adamlar da bütün ömürlerini edebiyat yaparak geçirmişler. Benim de aklımda sayısalcı diyorlar şimdi gençler. Ya bu insan niye edebiyat yapar? Tamam okuyorum, hoşuma da gidiyor romanlar falan ama insan niye hayatını edebiyatla geçirir? Rasim Özdenören'den bir randevu aldım. Devlet Planlama Teşkilatı'nda çalışıyordu, genel sekreterdi. Gittim. Buyur dedi, böyle babacan birisi. Dedim ben size bir sorun var, o yüzden geldim. Buyur nedir sorun dedi. Böyle bir masada oturuyoruz. Bunu burada 2. defa anlatıyorum şu platformda. Kocaman bir toplantı masası var. Bir tarafta ben, bir tarafta o oturuyor. Dedim ki insan niye edebiyat yapar? Edebiyat ne işe yarar? Can you get the translation? What is literature for? Edebiyat ne işe yarar? Hiç duraksamadı. Dedi ki, şimdi bak dedi. Sen dedi masa diyelim ki 1 metre. Sen masanın bir tarafındasın. Diyelim benim tarafımda bir pire var. Pire. Sana doğru sıçrıyor ve sana doğru ulaşacak. Ama algoritma şu. Her defasında aradaki mesafenin yarısı kadar sıçrayabiliyor. Mesafede 1 metre. Kaç sıçramada sana ulaşır? Ben de hiç duraklamadım, ulaşamaz dedim. Yani cevap ulaşamaz, sonsuz. Evet dedi, bildin dedi. Nasıl bildin dedi. Ben de bunu matematikten biliyorum. Lise matematiği bu. Limit. Dedi, evet dedi, ulaşamaz dedi. Sen dedi matematik dilini biliyorsun. Sen bu çözüme oradan ulaştın. Edebiyat da dedi, bu pirenin sana asla ulaşamayacağını gösteren bir başka dildir dedi. Ben de tamam dedim. Çayımı içtim ve ayrıldım. Şimdi Feza Bey'in benim anladığım kadarıyla dehası bu dili biliyordu ama öbür tarafa da yani bilim dili, matematik dili, yani Newton'un dili diyelim ona, matematiğin, fiziğin matematikleştirilmesi. Siz çünkü onun üzerinde çok durdunuz hocam. Yani şu yöntemi öğrendim, şunu öğrendim ve o kelimeyi sizden duymak, sizin gibi genç birisinden duymak çok önemli. Çünkü öğrenmek çok önemli bir şey. Hani Descartes diyor ya, ben düşünüyorsam varım. Biz onu biraz değiştirtip bir kitap da yazdık o konuda. Düşünmek mi, öğrenmek mi? Öğrenmek daha üst bir aktivite gibi. Yani daha üst, daha elit bir aktivite gibi. Çünkü kavramayı, düşünmek başka, kavramak başka, öğrenmek başka. Şimdi sanki Feza Bey'i çok tanımak isterdim yüz yüze. Sanki onun dünyası sadece fizik değil, metafizik de var gibi. Yani çok daha geniş bir dil ailesine sahip gibi bir insandı. Ve her şeyden önce de bütün aile insandı. Hepsinin ruhu şad olsun, Allah hepsine rahmet eylesin. Biz de ne mutluyuz ki işte burada kendisini anıyoruz, yüceltiyoruz. Benim anlatacaklarım bu kadar.
Sayın Rektörüm çok teşekkür ederiz efendim. Ve şimdi de konu başlığı evrenin doğumunda termal enflasyon olan İzmir Yüksek Teknoloji Enstitüsü'nden doktor öğretim üyesi Hee-Sung Zoo'yu davet ediyorum efendim kürsüye. Buyurunuz.
Is this working? Merhaba, benim adım Hee-Sung. Ben Güney Kore'den geldim. Hoş bulduk. My name is Hee-Sung, so I'm working in İzmir Yüksek Technology Institute. Today, I'm going to talk about my research topic, so-called thermal inflation. Actually, this device exactly 30 years ago, and then still I'm working on. Actually, I didn't make this. Actually, my PhD advisor made this. Okay. Okay. So when I think about this conference, the first word that comes to my mind is this one: inheritance. Türkçe miras. Inheritance. So if I find some photos about inheritance of Turkey in Googling, then I find this picture. Yes, this is the inheritance of your ancient kingdom and ancient history, right? But if I go to the Oxford Dictionary, then there is a definition of the inheritance. First one, the money, property, some physical property that you receive from somebody when they die. Okay, so maybe something like this, but with something more, something from the past, probably from your family, your old generation, that affect the way you behave, you look, you do some work, you do science, like that. So I think this is important definition of the inheritance. So when I think about this word, inheritance, then I come to think about my PhD advisor. So this is me, and this is my PhD advisor. Actually, he studied England, and then after passing through some career, and then finally he came to Korea. And then, you know, I learned various physics from him. But, you know, think about this. As a Korean, I am learning physics in Korea from foreign professor. So in the same way, here I'm working as a foreign professor teaching Turkish students. So, you know, I came here, you know, easily. I can decide easily. Probably my advisor was also foreign faculty, so maybe that affects my life. Okay? So thermal inflation is devised by these two authors. So as I told you, Professor Yuan Stewart is my PhD advisor. David Lice is his advisor. So they are actually Lancaster people. So they made a so-called thermal inflation from these papers. Okay, so I know, so here the people have very different backgrounds. So I want to make my story very easy. So first topic to cover is so-called the power spectrum. Let me do this. Yeah, so think about this wave, you know, we find various types of wave on string, on water, you know, you can hear my voice because my throat is vibrating air and then this wave comes to your eardrum, okay? But there is very interesting picture here. So you are thinking about wave 1, wave 2, they are moving into toward. Well, they meet in the center, then you will get some bigger wave, okay? Then after some more time, this wave just passed through, okay? The original form does not change, okay? But think about it, you have one thing and the other thing combining together. It might be distorted, it might be changed, but actually they are not changing, they are not modified, okay? This is important property linearity, okay? So this principle looks very simple, but is still valid in various physics or science, even in quantum mechanics. Okay. Think about this. So there are some people, they are singing together, they are playing musical instrument, but your eyes actually can hear all of those sounds together, okay? So for example, if I say something, but Suatoja is thinking something, then his voice is distort my voice and my sound, then we can hardly understand what's going on here, what I'm talking about here, right? But when you look at this wave has that kind of very interesting properties, linearity, okay? So think about this, if we think about the light, okay? Then actually light is a kind of combination of another light rays with different frequency, means colors. So if you shine the light through this prism, then you can find the various colors and colors, okay? So this is wave, okay? So for example, if you think about this square wave means something like this. Okay, you have that wave, right? But interestingly, by using only these sine functions, you can actually generate this, the shape of the wave, okay? So here, sine wave, and actually you can add up, so the sine wave, different frequency, wavelengths, like that. And then we have some kind of power. So you know this, what is this? This is Fourier series. Okay, so if you have some kind of periodic function, actually using cosine and sine function, you can decompose it, right? Decompose it to the wave, different wavelengths. Okay, here. Well, here actually this coefficient A and B, and they are important because they represent the power of those fundamental wave and the sine cosine wave. Okay, in this way, actually you can specify the pattern of your wave effects. Okay, let's do that. Okay, so think about these two cases. So if you have sawtooth wave, just like this, sawtooth wave, and you are considering another triangle wave, can you distinguish these two waves? Yes, right? They look different. But we want to say more accurately or more generally, then what you are going to do is this. Using fast Fourier transform or Fourier series, actually you can find those A and B and coefficient here. Okay, it is called power spectrum. So here x-axis is about frequency or wavelengths related quantities. Y-axis is about that kind of a power. Okay, so for a given signal, the power spectrum gives a plot of portion of the signal's power falling within some given the frequency bands. Okay. So for example, now we are thinking about this 4 different sound: tuning fork, flute, violin, and human voice. Yeah, they are making same pitch, but actually, if we analyze their waveform, definitely the forms are different, even though they are playing the same pitch. Okay, but if you do Fourier transform, and then if you try to find power spectrum, then actually the tuning fork gives this one, and flute this one, violin this one, singer this one. So they are different. So if you analyze power spectrum, actually you can capture the main feature of your distribution of a wave or something like wave. Okay. So power spectrum is very, very useful. Okay. So power spectrum is this. If you have some distribution of some matter or some sound or spatially or temporally, then actually you can decompose all of those patterns by using some kind of unit wave, cosine or sine or exponential something. Well, each of these fundamental cosine sine will give having some kind of wavelengths. Then this x-axis about wave number is k. Actually, it is 2 pi over lambda. This is 1 over wavelengths. N is power. Then you can specify some pattern by using power spectrum. So I am studying cosmology. So this is very interesting and simple and practically important object. Okay. So this is a cosmological history, well developed and well organized. So probably we will have some kind of Big Bang and then inflation. And then after then, probably as the universe expands, initially we have some kind of plasma of all the matter. But as time goes on, the photon decoupled. And that photon will give some kind of pattern, which is called cosmic microwave background here. And then universe evolve, and then we will see various structure. Okay. Actually, here we see some kind of pattern here. And at any time, you can find some kind of distribution of matter or photons or some dark matter or something like that. Okay. So anyway, so we can get that. So for example, if we think about this one, cosmic microwave background, then, you know, this is what actually you are looking at these, all the direction from the Earth. And then this is primordial photon. This is not coming from your sun, okay? And then this is primordial photon hovering over the whole universe, then you will see that photons in the all direction. Then average temperature is quite low, it's 2.73 Kelvin. But you can find the fluctuation level of 10 to the minus 5, okay? So now you see this pattern, then what can you do? Actually, you can use something like a fast Fourier transform, then you can find a power spectrum like this. So this is a statistical picture of your cosmic microwave background, okay? And so, you know, this is what? This is the galaxy map, okay? Using nice telescope, we can collect the, we are observing the galaxy over the universe. Then you can find this map. We find another pattern, and then we see that pattern, and then we want to specify what is this exactly. Again, we are going to use power spectrum. Then actually we will get this form of the power spectrum. This is a matter distribution like galaxies, okay? So here, actually this red dot is about the galaxies. Combining some other data, so we can construct this galaxy, power spectrum of the galaxy distribution, okay? Is it easy to understand? Okay, so our primary concern, simple cosmology, is to find power spectrum and then discuss the power spectrum. Okay, cosmological power spectrum is x-axis about wave number, so y-axis is about power. Okay, again, this k means actually one of the wavelengths. Okay, but in the cosmology, we should give a kind of a unit of distance. This is parsec. Parsec, 1 parsec is 3.26 light year, or 3 times 10 to 13 kilometer. Okay, but here, x-axis is about the inverse of your length scale. So if you have a high k mode, then you mean this is small distance. If you go to the small wave number, then you will get large distance. Okay? All right. So in the beginning, we are thinking that there is a inflation here. So actually this idea of the cosmic inflation is made by Alan Guss at MIT. So he introduced this kind of a model, okay? We needed to introduce some substance to make inflation, okay? In physics, we are putting some kind of potential for that kind of substance, okay? Then we are using this potential. And then here, initially, your field is at this plateau, okay? Here, this amount of energy is called vacuum energy. This vacuum drives the accelerated expansion of the universe, and then making our universe isotropic and flat, okay? But, here, actually, your substance may have some kind of quantum fluctuation. So it is fluctuating. Then this tiny fluctuation will give seed for the structure formations. Okay? So that's the idea of the cosmic inflation. Then, actually, we are going to do this. This is the Einstein equation. And then you put, firstly, metric tensor, and then scalar field. And then we give a kind of fluctuation. Then here, this average motion or coherent motion will give accelerated expansion of the universe. This perturbation will give cosmological perturbation, explaining that small fluctuation. This is a seed for the structure formation. As time goes on, this seed is grow, then we find the universe like that. Okay? So make everything simple. So anyway, so if you calculate this inflation model, then at the end of the day, you will get some kind of power spectrum, which is very simple. It's like some kind of a straight line. Okay, that is typical picture of the power spectrum for cosmic inflation. Okay, but this power spectrum can be checked with the cosmic microwave background power spectrum. So if we combine this, so this is most probable constraint for the power spectrum of the inflation. So the inflation power spectrum has no problem with cosmic microwave background. Okay, that's the point. Okay, all right. So standard inflation cosmology. So here, actually, we don't know yet what is happening in the Big Bang, but we will have some kind of inflation. And then we should develop some kind of mechanism to explain various unsolved questions. And then after passing through those eras, so we will find some formation of the universe structure. And then, yeah, like that. Okay, this is a standard inflation cosmology. But what if you put supersymmetry, then probably we will have a better idea explaining the era around the Big Bang. That's good because we can develop some theoretical framework to describe Big Bang moment, and we can find some consistent cosmological history. But however, if you put supersymmetry and string theory at that region, actually you will have very severe problems, so-called moduli problem. We will find another particle, moduli. It gives disaster, actually. Why? So again, so I will introduce some substance field to describe this moduli field. Actually, its potential is something like this, and then our moduli field move along this. But if you consider the high temperature of this moduli field, then the potential is deformed like this. Then, actually, as time goes on, in the high temperature, we have this potential. In low temperature, we will go to this form. Then, when you think about this black, this one is particle, it can roll over the particle potential. Then, actually, it can oscillate in this way. Okay, and this oscillation quite strong, and it dominates the energy content of the universe. Then actually from that energy release huge amount of entropy, then it disturbs very, very critical mechanism, so-called nucleosynthesis, to making heavier element in the universe. Okay? Yeah, so that's the problem. Okay, so let me summarize this. We have some kind of a nice story about the inflation. But if you turn on this string theory or supersymmetry, then we will have moduli problem. Then this moduli problem will spoil all the successful scenario of the universe. So that's the problem. Okay. So moduli generated, it is a kind of disaster. It spoiled everything. So we need to save our cosmological scenario by introducing some nice idea. So that is thermal inflation. Okay. So thermal inflation starts from this. Actually, we are introducing some kind of potential like this. But here, this minimum point is quite far from the origin. Okay. Here, actually, if you add temperature effect. Why? Because all the universe will be very, very hot. So if you put that kind of temperature effect, then the potential is modified in this way. Then actually, this field is here. Okay? Captured, trapped at the origin. But as temperature goes down, finally, this vacuum energy of this one drives another inflation. Okay, so this is important. This will dilute all the modular fluid. Do you remember? The oscillating particle will be removed, diluted by this mechanism. Okay. After that, actually, the potential is becoming like this. We have some kind of potential barrier. Okay. Then, you know, in the quantum mechanics, actually, we can think about the quantum tunneling. Actually, this is a bit different, but anyway, we may have the tunneling. Then, you know, this process is a kind of first order phase transition. And then we will see some kind of bubble generation. And then we will see gravitation wave background. Okay? And then finally, our field phi will be oscillating here. And then it passed to the correct history to the radiation domination. Okay? So this is made by my PhD advisor. Okay. So let me give you a kind of summary. So without inflation, thermal inflation, if you have a primordial inflation, and then inflation decay, and then we reheat the universe, and we have radiation dominate universe, that's it. That's okay. But to resolve the modularity problem, if you add thermal inflation, then cosmological history becomes different. So between this 1 and 5, we should put 2, 3, 4. So initially, we permit modularity particle dominated, and then we activate thermal inflation, and then we go to flatten domination, meta domination again. So, yeah, the original idea is this. So here, actually, for the simulation working correctly to resolve the modularity problem, then we have some kind of constraint. So NTI means the folding, how much universe expand during the thermal inflation is like a 10, then that's enough to resolve the problems. Here, there is important point. So what is going to do, what is the thermal inflation is going to do for the perturbation, power spectrum? Actually, the thermal inflation does not change much, but it touches very, very small scales. So it does not change the original power spectrum so severely. Okay, that's the point. Okay, and 2012, I have some question about this. Then I discussed with my advisor, and then I asked this: if this is true, then can you prove your idea about the thermal inflation by looking at this small-scale effect? So that was the question, and then I discussed with him a lot. Well, initially, his response is very bad. Okay, it might be working, but it is too small. We may not see any observable effect. Okay. Let me skip this. So after 3 years, so we got some result. Okay, we tried to solve this one. So due to the thermal inflation, power spectrum is changed from the original inflation forms. How much? So firstly, we needed to introduce one characteristic scale, KB. Okay, that's important. And then, so we can calculate some mathematics. And then finally, we can find this complicated formula. But the formula is not so enough to see. So the picture is this. So thermal inflation modify the power spectrum this amount. So again, so this x-axis is about wave number. If you go to the small number, it means large scale. But if you go to large number in wave mode, then you will get small scale. Okay. So here, if you go to the 0, the small number, then it is just 1. It means it does not change much. But we have some kind of enhancement around that KB, we introduce KB. And then suddenly it's suppressed and oscillatory. Okay, that's the main result. Okay, so if I draw a few power spectrum of thermal inflation, is this. Okay, KB is 10 megaparsec inverse, 100, 1,000, and 10,000, etc., etc. So enhancement and suppression and some oscillatory. Okay, that's the main result. So finally, we calculate this, and then we see this result. But, actually, this is important to plot. X-axis is about wave number. Y-axis is the power spectrum, power. But this gray region is what? Actually, the region excluded by some kind of experiment or observation. So CMB, cosmic microwave background, or large-scale structure, then you can find this white region is safe. So if you provide a kind of successful theory for the cosmology, then your power spectrum should be around this white region, okay? But if you go to the small scale, then actually we don't have much constraint. Well, it depends on the scenario of the dark matter. Then we may have some more additional constraint. But if the dark matter species is quite different, then we may not apply that constraint. So white region is here. So our conclusion is this. Actually, standard cosmology is something like this, this black line. This is a power spectrum. Okay? Our thermal inflation is what? It's something like this. Slight enhancement and suppression, like that. Okay? So these two standard cosmology with having primordial inflation and with the thermal inflation cosmology, they are different in terms of power spectrum. Okay? So to look at which one is correct one, so we should study the small scale structure, small scale parts. Okay? So after this paper, I work with him, and then I work with some other people. Then, from the CMB spectral distribution and small-scale galaxy substructure and 21 centimeter hydrogen power spectrum, another power spectrum. And the other guys did some simulation, and then we discussed this. And then nowadays, I am studying Lyman alpha simulation with some other guys. Okay. So in this way, I try to confirm that thermal inflation power spectrum. But it is not so meaningful because if this KB is not very large scale, actually it does not have any observable effect in this all of topics. So a bit frustrated, but in some sense, the thermal inflation is not quite different from original or primordial inflation. Okay. And then a few years later, we wanted to refine our result further and further. And then, in 2015, we tried to solve this equation analytically, so we get some solutions. But we want to discuss or consider some generic cases. Then we get, some interesting figure. This is a power spectrum, and the color means some kind of different parameter setting. Okay, but the typical cases for the successful thermal inflation, this epsilon value is very small, like 10 to the minus 16. Okay, but if you go higher, then the power spectrum is different. When you look at this figure, can you find some kind of tendency or some principle? So I cannot get any idea. But one night, I got revelation. So here, actually, we express our power spectrum in terms of K over KB. Okay, But there is another characteristic scale in the sum manipulation scenario. But instead of KB, if we use KA, then we get this kind of picture. Okay. So is it beautiful? To my side, it's beautiful because we find definitely some kind of enhancement, oscillation. But if you take a different parameter, then actually our power spectrum is increasing at certain point. Okay, that's the very, very different, conclusion. So compared to the 2015. Okay. So in some sense, if you change the angle where we are looking at, then we can get the beautiful, understandable, more understandable picture. Okay, like that. Now we are studying more general case. Initially we are thinking about moduli, capturing here and then oscillating here. So this moduli potential will give a kind of effect on the power spectrum. That was our guess. And then we continue to study. This is a real horrible work. Equation is really complicated. So we developed some kind of a code or numerical code to see this effect. Still is very, very different and challenging. Okay. But when you look at this, if you change our sum manipulation parameter, then we will have some kind of evenly oscillating part. But if you decrease this number, then we will get something distortion. And then if you consider a bit bigger, then we will have more distortion. Okay, like that. So this is in progress. Okay. So this is a kind of a review of the development of sum manipulation for last 30 years. So initially, in 1995, so my advisor devised sum manipulation to get rid of moduli effect. Moduli, dilute, remove, resolve the moduli problem. But at that time, the power spectrum would be changed a bit, but it is about very, very small scale. Probably they are expected to be negligible, not worth details. Okay. And then between 1995 and before 2015, we have another work developing some particle physics model, baryogenesis, and bubble dynamics like that. And then finally, 2015, we computed sum manipulation power spectrum within typical parameter space, so relevant for the normal typical sum manipulation. And then 7 years later, we extended our analysis to even smaller scale. Okay, and then this year we identified this moduli oscillation effect. Actually, this is appearing at the even smaller scales. So it means what? Even though sum manipulation was originally introduced to eliminate all the moduli, actually there is some kind of effect in the power spectrum. Okay? But these scales are so tiny, so detecting this effect may remain beyond our observable reach. Okay? So, this is my journey. So let me summarize this journey in one sentence. Okay. Catch moduli if you can. Okay. So this is my students, and here there are some Korean speaker. Actually, we are organizing, winter school in every February. So we try first workshop. So we will develop it as an annual model. So I am studying some other issues with my students. Well, I want to say this. Actually, I am not so directly related with the Feza Gürsey Hoja, but when I look at this picture, he is going to try to speak about some particle physics and gauge groups like that. But when I think about my cases, actually my advisor give me some kind of research topic and we write some papers. But there must be something more than this. I am learning how to tackle our research problems, numerically, analytically, repeated again and again, like that. So inheritance, I mean, Feza Gürsey give us some nice word, nice paper, renominated all around the world. But I believe he gave us a kind of inheritance. So I want find it, and then based upon this, maybe you can develop a more beautiful culture in Turkey. But this is a physics. Physics is a small problem, but I mean, this kind of inheritance is quite, I mean, commonly valid for all different branches of the science and technology. Okay, thank you for listening.
Evet, çok teşekkür ediyoruz doktor öğretim üyesi Hyesung Zo'ya. Efendim, şimdi ben son konuşmacımızı anons etmeden önce kıymetli hocam Profesör Doktor Tekin Dereli'yi maalesef uğurlamak zorundayım. Çünkü kendisinin uçağı var. Az sonra havaalanında olması gerekiyor. Bugün için kendisine çok teşekkür ediyoruz tekrar efendim. Suat hocam size eşlik edecek hocam. Tabii hocam. Sizleri de.
Teşekkür ederim herkese.
Çok teşekkür ederiz hocam. Ayağınıza sağlık tekrar. Çok memnun olduk. Efendim, son konuşmacımızı anons edeceğim ve sizleri kendisiyle baş başa bırakacağım. Video konferans yöntemiyle kendisiyle bağlanacağız. Evet, Tekin Dereli hocamı uğurluyoruz. Efendim, son konuşmacımız video konferans yöntemiyle programımıza katılım sağladı. Kendisi Kapadokya Üniversitesi'nden Profesör Doktor İskender Öksüz. Bugünkü konu başlığı Gürsey'li hatıralar olacak. Ben Sayın Hocama mikrofonu uzaktan bırakıyorum. Buyurunuz hocam.
Teşekkür ederim. Ben de OSTİM'e kadir şinaslığından dolayı teşekkür ederek başlayayım. Feza Hoca'yı anma fırsatı verdiğiniz için bizlere. Efendim, ben 1962'den başlayacağım. İnsan kocayınca böyle oluyor, eski gidiyor. Evet. 1 yaşındaki bir fen fakültesi, Ege Üniversitesi Fen Fakültesi. Şimdi Feza Hoca ile ne ilgisi var? Göreceksiniz Feza Hoca ile ilgisini biraz sonra. Genç bir şeyler yapmak isteyen idealist hocalar. Biyolojide Yusuf Vardar var. Efendim, kimyada Burhan Pekin, Emin Dikman, Gürel Nişli, daha ismini saymadığım birçok ve hepsi idealist öğrenci diye çırpınıyorlar. Birilerini geçiştirmek için çırpınıyorlar. Astronomide Abdullah Kızılırmak, matematikte Masatoshi Ikeda var. Sonra Gündüz Ikeda oldu. Efendim, Yusuf Vardar Hoca yine 1-2 yaşında olan o tarihte TÜBİTAK'la sıkı temas halinde. Ve bizleri parlak öğrencileri diyeyim, TÜBİTAK'a yönlendirmek istiyor. TÜBİTAK burslarına yönlendirmek istiyor. 1963 veya 64 yılları olmalı. Tam hangi yıl hatırlamıyorum. Biz 3 Ege Üniversiteli, Ege Fenli öğrenci TÜBİTAK üniversite burs sınavına gittik. TÜBİTAK o sırada dediğim gibi yeni kurulmuş. Türkiye Büyük Millet Meclisi'nin arkasında Havuzlu Sokak diye bir sokak var. Orada bir bahçeli ev. Bu TÜBİTAK'ın merkezi. Evet. Bahçe içinde bir ev. Ve jüri. Jüride Feza Gürsey, Erdal İnönü efendim. Diğerlerini hatırlamıyorum şu anda. Ve soruları daha çok Feza Hoca sordu. Tabii benim elim ayağım titriyor. Hani mülakat demişler ya, bu mülakatın alası. Sorulardan biri şuydu. Türk bilim adamlarından, madem ki bu işlerle uğraşıyorsun ve bu kültürün de olması lazım, Türk bilim adamlarından kimleri tanıyorsun, kimleri sayarsın? Ben gayet mahcup efendim, işte çoğu bu odada zaten dedim. Ve nasıl? Şöyle, siz Ege Üniversitesi'nde konuştunuz dedim ki, hakikaten de gitmiştim Gürsey'in konuşmasına. Ne anlattım dedi. Şimdi bu çok daha zor bir soru. Bugünkü konuşmalar gibi bir konuşma çünkü. Yani fizik konuşması oradaki de. Aklımda kuvvetle kalmış bir benzetmesi var. Feza Bey'in. Bir uzaylı gelse ve ondan ilk mesajları teati etsek, alıp versek efendim, neden bahsederiz? Boyutlar, efendim, yön filan, hepsi bunların görece. Spin sağlam. İşte. Yani sağ spinlen sol spin, işte up spinlen down spin. Burada yanılmayız. Efendim. Evet. Güzel. Onu geçtim böylece. Ve bu arada bir Heisenberg lafı etmişim. Hemen hoca girdi araya. Ne sorarsınız Heisenberg'i telaffuz eden bir öğrenciye? Şunu sordu. Heisenberg hayatta mı? Dedi. Üniversite 2. sınıf öğrencisi. Heisenberg hayatta mı? Hayatta dedim. Dua ediyorum son gördüğümden beri ölmesin. Görmedim tabii hiç Heisenberg'i ama. Nereden biliyorsun dedi. Ve benim öldürücü cevabım şuydu. Geçen ay Scientific American'da makalesi çıktı dedim. Hakikaten Scientific American okuyordum ve Heisenberg'in makalesini okumuştum orada. Bu galiba hani that clinched it denir ya, bu işi bitirdi. Ve ben bursu aldım. Burs şöyleydi, hala var mı o burslar bilmiyorum. Bay grubunun, bilim adamı yetiştirme grubunun verdiği bir burs. NATO ile de bir ilgisi vardı zannediyorum, para oradan mı geliyordu. Üniversitede verilmeye başlıyor ve iyi bir burstu. Yani miktar olarak yüksekçe bir miktardı. Babam memurdu, 1000 lira maaş alıyordu. Benim bursum 900 liraydı falan, yani çok ciddi bir paraydı. Bir de şu madde vardı, başarının devamı halinde yurt dışı bursuna dönüştürülecek. Başarım da devam etti herhalde ve ben kendime birçok yere müracaat ettim, birçok yerden kabul gördüm. Referanslarınız iyiyse, notlarınız yüksekse, paranız da cebinizdeyse, yani bir burs almışsanız, o kadar zor değil tabii doktora için başvurmak. Hocalardan biri galiba Dereli hocaydı, master'a değil doğrudan doğruya doktoraya yöneldim diye. Amerika'da da öyle, yani master'ı bir nevi teselli ödülü gibi alıyorlar. Esas temel bilimlerde doktora önemli. Ve o tarihlerde Sinanoğlu meşhur bir isim. Çok genç profesör olmuş Yale Üniversitesi'nde. Ve ben kendime New Haven'da Science Hill denilen Sterling Chemistry Laboratory, Sterling Kimya Laboratuvarı'nda buldum. Önünde Sterling'in heykeli vardı. Sterling ne yapmış? Petrolün işe yarar bir şey olduğunu göstermiş ve işe yaratmış. Öyle biliyorum. Sterling Chemistry binasının karşısında fizik bölümü var. Fizikte de Feza Gürsey var. Evet. Sinanoğlu ve Gürsey. Biri daha yeni çok elektron teorisini çıkarmış. Many Electron Theory of Atoms and Molecules diye. Öbürü SU6 ile SU6 ile meşhur. Evet. Ve dünya grup teorisiyle yapıp kalkıyor. Bir de laserla o tarihlerde. DNA'nın strüktürü de yeni çıkmış. Sinanoğlu güneş tayfında kuark enerji seviyeleri arasında geçişlerin çizgilerini arıyor. Ve bu arayış Physical Review Letters'ta yayınlanıyor. Letters biliyorsunuz Physical Review'dan. Physical Review hala öyle midir? En iyi dergisi, yani en prestijli dergisi fiziğin. Letters'ta hani gecikmesinde zarar olacak, hızla yayınlanması gereken şeyler için de Physical Review Letters'ta yayınlanıyor Sinanoğlu'nun paper'ı. Evet, karşı binada Feza Bey var. Uzaklarda bir yerlerde de işte Behram Kurşunoğlu'nu, Asım Barut'u falan duyuyoruz. Benimki bir bilim konuşması değil. Mesela Behram Kurşunoğlu deyince rahmetli Sinanoğlu'nun bana anlattığı Behram Bey İngilizce ile Türkçe arasında birebir tercüme yapmaya meraklıymış ve heyecanla o günlerde telefonla olmalı bildirmiş Oktay Bey'e jerk kelimesinin Türkçesini buldum diye. Hırt. Evet. Efendim, şimdi düşünebiliyor musunuz? Bir tarafta Oktay Sinanoğlu, bir tarafta Feza Gürsey. Biz 3 tane Türk doktora öğrencisiyiz kimya tarafında. Karşıda şey var, Alpar Sevgen var. Beraber gelmiştik onunla. Biz süper insanlar, süper Türklerdik. Bir sınav zor gelmişti sınıfa. Sinanoğlu'nun sınavı. Bizim öğrencilerden biri, benim sınıf arkadaşlarımdan biri kalkıp Joe diyordu, unutmadım. İskender bile zor dedi bu sınava dedi. Even İskender said it was difficult. Sinanoğlu da beni yanına çağırıp ya sen isyan mı çıkarıyorsun bize karşı diye şaka yapmıştı. Fakat hoşuna gidiyordu tabii. Efendim Derek de Sola Price bir bilim tarihçisi. O da Yale'de o sırada. Küçük Bilim, Büyük Bilim kitabının yazarı. İlk büyük bilim örneği olarak da işte şeyin rasathanesini, Ulu Bey'in rasathanesini verir falan. Devlet destekli bilim. Şöyle bir cümle var kitapta. Bilimde verimlilik kişi başına GSMH gayri safi milli hasıla ile ilgilidir. Ama Türkiye gibi istisnalar var. Evet. Ben de çok şanslı çıktım. Girdiğim yılın ertesi gün 3 paper birden yayınlandı. Bir tanesi Physical Review Letters'ta yine. 3 tane doktor öğrencisi dedim. İşte Profesör Önder Pamuk, Profesör Timur Halıcıoğlu ve ben. Biz de gittik ODTÜ'de teorik kimyayı kurduk. Ama bir direnç vardı, tutmadı da. Fakat öğrencilerimiz çıktı. İşte Şakir Erkoç, Profesör Fizik bölümünden emekli oldu. Şefik Süzer, belki tanıyanınız vardır. Ersin Yurtsever, Turgay Uzer. Bunların hepsi Türkiye'de, Turgay hariç. Evet, şu geldi aklıma konuşmalar sırasında ve bilim adamlarının kendi hocalarına yaklaşımı sırasında. Sanki bir miras bu da. Yani hocadan yetiştirdiği doktor öğrencisine bir miras, hatta bir genetik miras sanki kalıyor. Şakir'in bir öğrencisi profesör olduğunda gel dedenin elini öp diye bana getirmişti hocayı, yeni taze hocayı. Evet. Efendim, Feza Bey'in de Broglie'ye çok kızdığını hatırlıyorum. Yani Fransız fiziğini batıran adam diye bahsederdi. Hani dalga boyu falan vardır ya. Schrödinger idare eder filan. Ama illa esas kuantum dendiği zaman Heisenberg ve daha sonra da Dirac. Şimdi enteresan bir tesadüf. Heisenberg'in, ben öğrencilerime 1925'te bu iş bitmişti diye öğretirdim. Sonra baktım, asıl tarihe baktım. Heisenberg'in kuantum mekaniğini bitiren yayını, makalesi Zeitschrift für Physik, Almanca fizik demek lazım. Yayımlandığı tarih 9 Temmuz 1925. Bugün yani. Tam 100. yıldayız. Ayına kadar, gününe kadar. 9 Temmuz 1925. Başlığı da hareket ve mekanik ilişkilerin kuantum teorisiyle yeniden yorumu. Über quantentheoretische Umdeutung kinematischer und mechanischer Beziehungen. Evet. Efendim, tabii hem Yale'de hem ODTÜ'de şöyle bir kuralda söyleyebilirsiniz. Süha Hanım'ı görmüşseniz Feza Bey de yakınlarda bir yerdedir. Tersi de doğrudur bu iddianın. Feza Bey'i görmüşseniz Süha Hanım da oralarda bir yerdedir. Yusuf rahmetli çok genç o tarihinde. Şimdi tam tarihini bilmiyorum ama 12 yaşında, 13 yaşında, 14 yaşında falan olmalı. Eğer Yale'daysa 12, yok eğer ODTÜ'deyse 14 yaşında falan. Ve Süha Hanım bir gün övünerek Yusuf'un kendi icat ettiği bir fıkrayı anlatmıştı bize, bana efendim. Fıkra şöyle: sadist mazohiste ne demiş? Cevap: sana anestezi vereceğim. Evet, bu Yusuf'un 12 yaşında kendi bulduğu bir fıkra herhalde. Ben 20 dakika konuşacağım dedim. Galiba o kadar da oldu tam. Efendim. 1968'de SU6'den dolayı, inşallah yanılmıyordum, TÜBİTAK Feza Bey'e bilim ödülü verdi. Ve o konuşmasının, ben konuşmayı dinlemedim. Fakat manüskrisini bir şekilde elde ettim veya bana verdi belki de Feza Hoca. Başında bir dörtlük vardı. Dörtlük şöyleydi. SU6 düşüneceksiniz. Muhiddinem dervişem, hak yoluna girmişem, 18.000 alemi bir zerrede görmüşem. Feza Bey bu dörtlüğü konuşmasının sonunda okumuş. Sonra şimdi araştırdım, gazetelerde filan var. Evet, bu da edebiyat tarafı işin. Bu kadar efendim benim anlatacaklarım. Teşekkür ederim.
Efendim, kıymetli Profesör Doktor İskender Öksüz, gerçekten bugün bu anılarınızla etkinliğimize çok büyük katkıda bulundunuz efendim. OSTİM Teknik Üniversitesi olarak size çok teşekkür ediyoruz. Destekleriniz ve katkılarınız için. Efendim, birinci oturumumuzun sonuna geldik. Değerli hocamın da son keyifli anılarını dinledik. İkinci oturumumuz 10 dakika sonra yine aynı salonda devam edecek. Bu sefer uluslararası misafirlerimiz ve konuklarımız olacak. Sizleri de burada tekrar görmeyi arzu ediyoruz. Çok teşekkür ediyoruz. Çok sağ olunuz. Sevgili hocam, çok teşekkür ederiz.
Ben teşekkür ederim efendim.
İkinci oturumumuzun başlığı da modern bilimdeki son gelişmeler olacak. Bu noktada bizlerle beraber olacak Groningen Üniversitesi'nden Anupam Mazumdar, Ohio State Üniversitesi'nden Dr. Naim Göksel ve University of Southern California'dan Itzhak Bars bizlerle beraber olacak.
Can you hear me?
Duymuyor.
Kendi mikrofonu. Yaz. Anupam, can you hear me?
Yeah, I can. Can you hear me?
Yeah. So sorry for this late start because actually the previous talks extended, so that's why.
No, that's perfectly good. Don't worry.
So I will give actually the moderator, so she will guide the presentations. Okay.
Should I share my screen?
Yes, after a second, you can. Ladies and gentlemen. Okay. Can you hear us now? I believe you can. So, ladies and gentlemen, welcome back. We now begin our second session called Recent Developments in Modern Science. Our conference is being interpreted into 15 languages through the OMTI software developed by our software students. You can access the platform by scanning the QR codes available on the screens in this conference hall. So our first speaker is Professor Dr. Anupam Mazumdar from the University of Groningen, who will be joining us via video conference. His presentation is titled Spin Entanglement, Witness to Test Quantum Gravity in a Lab. Yes, the floor is yours.
Thank you very much. So let me share the screen. I hope, can you see my screen?
Yes, we can.
Okay, so thanks a lot for organizing this wonderful one-day workshop.
Okay, just a second. If it's possible for you, could you please do a full screen for the presentation?
This is the full screen on my laptop.
Oh, okay. Then it's okay. Okay, go on.
Okay, thanks. So yeah, so I will be talking about spin entanglement witness to test quantum gravity in a lab, and I would like to thank the organizers and especially Professor Suat for inviting me to speak in this commemoration workshop. So I will be talking about some recent development which I have been involved in. Is about how do we test quantum gravity in a laboratory. So in a very simple language, the question is, can space-time with matter be in two different places at once? And the talk is based on this paper of 2017. And then we have had another very interesting protocol, experimental protocol, to test this light bending experiment, which of course it has been seen, but now a quantum version of the light bending experiment can be realizable also, hopefully, in near future. And the research is funded by Gordon and Betty Moore Foundations, Sloan Foundations, and also by ERC and local grants from the Netherlands and from various other sources. So before I speak any further, let me first say a few words about Professor Feza Gürsey. I believe that his curiosity was truly foundational in nature. His focus was understanding the symmetry, the local gauge symmetry, and perhaps he was the main protagonist of symmetry. In all his research work, that was essential. He developed many beautiful models in physics, especially which has been extremely useful now in the context of string theory, grand unification theory, QCD. So way back in 60s, he gave the model for the chiral model. And then he's also recognized for his immense work in E6 and grand unification, which he did with his colleagues and his student at the time. And he also touched upon gravity. And he was one of the few physicists at the time who was concentrating on conformal gravity, especially in the Euclidean sector. He has looked into it. And it's also very sad that this year we had another great physicist who demised. He happens to be my colleague from South, from Utrecht, and Professor Gürsey, you perhaps know. He was a great practitioner of symmetry in all his research works. And in my opinion, he was extremely diverse physicist from Turkey. He has worked on many different aspects, string theory, ADS-CFT correspondence, hydrodynamics from symmetry principles, emergent gravity. So his focus was also based on symmetry. So you see that how knowledge gets transcended from one generation to another generation and so on and so forth. And I'm sure Umut was also very much inspired by Feza's work. And in all the works which people have been working on is to understand the nature. After all, as we know that, we live in, the universe is 13.8 billion years old. And we want to understand this universe. But it so happens that it's extremely complicated. We don't know the initial conditions. We make models, and sometimes these models have ad hoc assumptions. And, sometimes we look for simplicity as a physicist. And the reason why our colleagues like Feza and Umut and others have gone into symmetry, because symmetry plays an important role. It simplifies many of our understanding based on certain principles. So that's why people look for, and as a human being, we want to understand the entire cosmology of 13.8 billion years of entire particle spectrum. It's not an easy task. So we all want to simplify, and in this regard, I believe symmetry definitely plays a very important role. But also it is important to test some of our principles, some of our concepts, which govern our universe. And today my talk will be focused on the latter aspect, that how do we test certain aspects, certain features of our nature. So one particular aspect which I have been interested in recently is about space-time and gravity. The reason why is because it's, first of all, extremely old subject. It goes back from the date of perhaps even Aristotle, Galileo, Newton, and then in late reincarnation, Einstein and many other stalwarts have contributed towards understanding of gravity. And also perhaps Feynman's name will come at some point, and that's why I kept his picture. It's extremely fascinating. It is the weakest interaction of all. The interaction strength is the weakest, as we all know, and it attracts. It's an attractive force. Now, people believe that if you want to understand the real essence of gravity, we may have to go very close to Planck's scale or Planck time, something like which is impossible to achieve in our laboratory. And that's why sometimes people think that maybe cosmology might help to explore certain aspects of gravity and space-time. Or maybe in the context of coalescing black holes. But it's fair to say that we still do not understand what gives rise to this attraction. What is the origin of space-time? Whether it's classical or it is a quantum. Because we know that all other interactions which we have seen, like strong interactions, which Feza has contributed a lot in understanding, the strong interaction, electromagnetic interaction, weak interaction, we all know that it's inherently quantum, except gravity. We still do not have any concrete evidence for being quantum. So the aim, of course, of the future generation for us to test this very old topic of research, very old topic of curiosity. What is the nature of space-time? And can we explore this question in a laboratory, in a tabletop experiment? And as you will see towards the end of my talk, that this quest to understand the fundamental aspects of space-time will push us towards extreme quantum technologies, extremely disruptive quantum technology, which we have not seen at all so far, we might have seen it in science fiction, but hopefully in years' time, it will be a reality. So the plan of my talk is that I will talk a little bit about the foundations of quantum mechanics, macroscopic quantum superposition. I'll talk about the fundamental implications, especially towards the experiment which I myself have proposed along with my colleagues. It's known as quantum gravity-induced entanglement of masses. In short, it's called QGEM experiment. And I'll talk about the future outlook, and it has immense applications. Any experiment you take, whether it's CERN's experiment or LIGO experiment or any experiment, they all have applications one way or other. And if time permits, I will discuss a little bit about them. So coming back to the talk, let's come to the set up the stage. So in physics, we all look for correlations, especially when we want to look for observations. The previous speaker has spoken a little bit about cosmological observations, perturbations, and two-point correlations, and things like that. So we always look for correlations, whether it's a classical correlation or quantum correlation. Now, it turns out that the classical correlation is much simpler than quantum correlation because quantum correlation is much more richer because of the inherent uncertainty principle. So if you take two spins, you can correlate in the x direction spin in the sigma is a Pauli matrix, in the y direction between two systems. So A and B are two systems. So sigma xa, sigma xb, y x x x y x z, and so on and so forth. You can build the entire set of correlations, unlike in a classical correlation. In the classical correlation, if my thumb is up or down, that's the only correlation which I can set up. But in quantum mechanics, I can simultaneously set up many correlations. And it's my choice what I want to extract. Which information do I want to extract? I have a choice even. So in this respect, quantum correlation is much more richer. And one of the correlation in quantum mechanics is perhaps known as entanglement. Now, we know the definition of entanglement, a very simple way to defining it. On your left-hand side, if you have two systems, A and B, quantum systems, A and B are quantum systems. So the product state is the one where you can see that the wave function of A and wave function of B are separated. But when the wave function of A and B are non-separated, you cannot separate them. They are called entangled states. So you build correlation. So imagine you have got spin up and down. You are building correlation. Spin is spin up, up, up, down, down, down, down, up. All four possible combinations. And this entanglement is a bona fide quantum entity. It has no classical analogy whatsoever. Classical mechanics cannot replicate the concept of entanglement. So if I want to understand something inherently quantum, I must look for states such as entangled state. And it so happens that quantum interactions leads to entanglement. So in what sense it leads to entanglement? A very simple example I'm going to illustrate in the context of harmonic oscillators. Let's say that I have got two harmonic oscillators, A and B, and let's say that we work in a number basis. So the ground state is 0, 0. But when I switched on an interaction, then what happens? My wave function is going to evolve. And the wave function will evolve like this. On the right-hand side, I have written psi of f is the final wave function. It evolves as sum over n, Cn, small n, and capital N. Small n, capital N are my occupation number because the state has evolved from ground state 0, 0 to small n and capital N. Now, the final wave function, you can recast it in terms of product state and something which is non-product. So the product state, you can see that you got two terms, an summation of an and summation of bn, and I have added and subtracted, basically. So you see that if you look into the algebra, it's actually nothing but the Cn, small n, capital N, sum over n. So the final wave function, you can recast it as a product state. But on top of the product state, or in addition to the product state, you also have something called non-product state, because if that is the right-hand side term is non-vanishing, then the final wave function is entangled. And you can compute that, this coefficient C and M, by the overlap between your Hamiltonian of the states, ground state and the excited state. And as long as this coefficient C and N is non-zero, it tells you that your final wave function is an entangled state. Now, you see that this will be generically non-zero for interaction, generic interaction. And that interaction could be anything, could be QED, but it has to be quantum. HAB hat, it is a quantum operator. It could be QED driven, QCD driven, weak interaction, phonon interaction. And if gravity is quantum, then the interaction Hamiltonian which you would construct out of that will also lead to an entangled state between two harmonic oscillators because of the gravitational interaction. So from very simple one-page explanation, you see that quantum interactions always leads to an entanglement. It's inevitable. So if you create a macroscopic superposition in a laboratory, so a system is here and here simultaneously, this is sometimes called the Schrödinger cat state, which people have actually constructed in a laboratory. In atom interferometers, they have created a spatial superposition of 0.5 meter in Stanford, and now the thrust is to go for roughly a 1 meter atom interferometer. And now people are trying to create this superposition with macroscopic system, and that's something which I will talk today. The system is inherently quantum gravity. Because if gravity is quantum, then if the matter is, I know the matter is quantum, there's no doubt about it. But if gravity is quantum, then this system is inherently a quantum gravity system. And the interaction vertex, which we can all read it, is actually a tripartite entanglement between matter and graviton. So h mu is a graviton, is a small perturbation of your space-time, if I quantize that, and T mu is coming from your, basically your superposition, the fact that you have created a macroscopic superposition. It gives you a tripartite entanglement because you have mode function gk lambda will couple to x square, where x is your same as your matter. Now, there's another theorem which is called LOCC theorem, local operation and classical communication. So it tells me that as long as system A and B, if you take two systems A and B, which are quantum, if they are interacting purely through a classical channel, they are not going to get entangled. And this theorem was known to us since the days of 1996 due to Bennett, and many other colleagues have contributed. Charles Bennett is considered as one of the father figures for quantum computing. So LOCC theorem was known to the community. And when my colleagues explained me about the LOCC theorem, I immediately realized, hello? Hello?
Yes, we can hear.
But my stream has stopped working.
Oh, just give me a second. Is it still the same? Can you hear us?
Yeah, I can hear you.
What is the problem right now?
Can you see you can see my face, but you cannot see my screen. So somehow it has.
Okay, so I was just going to tell you that when you do a full screen, we are unable to see the pages that you skip. So it's better if you don't do full screen and do your presentation in that way.
Okay, I see.
Okay, could you please try that for us?
Okay, I can try it. Is it better now?
And yes, okay. Could you skip one page? At least we will see that the pages are going.
Okay. Oh,
yes, okay.
You could not see the pages before.
Yes, yes. Unfortunately, I didn't want to interrupt you, so we were listening only.
I'm sorry. This is very strange. Anyway, okay.
Sometimes it happens when there is a live broadcasting and then when you do a full screen presentation.
Okay, I see.
Okay, thank you so much.
You're welcome. No problem. So, okay, so I was talking about this tripartite entanglement just before, and then I spoke about this LOCC theorem, which is it's the no entanglement via classical mediator. So what it means is that if Alice and Bob, two quantum systems, if they are interacting purely through classical channel, they are not going to get entangled. So what can lead to entanglement, as you can see immediately, is that if you have two quantum systems in quantum field theory language, if they are interacting via a mediator, let's say in this particular case, X is your mediator, then your system, AC and BD, are going to get entangled, yeah, through purely a quantum channel. So very simple definition, as we all look for simplicity. And so a very simple definition for any theory of quantum mechanics and quantum field theory, in this particular case, quantum gravity, is actually this definition of LOQC. So LOQC stands for local operation and quantum communication instead of classical communication. So what it means is that it's the ability to perform quantum communication, hence generating quantum entanglement in quantum systems. And now that could be your space-time, could be your quantum system, or probes. So matter as a probe to quantum space-time can also get entangled. And it is impervious of how you quantize gravity. So it doesn't really matter how you quantize. Maybe you quantize perturbatively or via string theory approach you take, or loop quantum gravity approach you take, or dynamical triangulation you take. Doesn't matter. Irrespective of how you quantize your theory, the basic definition of quantum gravity is that its ability to communicate. So you have quantized a region of space-time, it will immediately communicate to its nearby regions as well. And this communication ought to be quantum. And as a consequence of that, the two regions of your space-time would get entangled. And so that is very simple and crucial definition. And when you want to probe something as fundamental as quantum gravity, is important to ask the basic question and test whether that basic principle holds true or not at the in any experiment or not. And this gives rise to our experiment, that now the challenge is that how do you create such an experiment? Because in general, if you take any object like us, like you and me or sun, we are so much entangled with the rest of the interactions, electromagnetic interactions, weak interactions, strong interactions. You need to disentangle all these interactions in order to extract the interaction, the entanglement due to gravity. So how do you achieve a real ground state of matter so that you can create, you can split the matter into this A and the position A here and there simultaneously? So this is the biggest challenge. And with technology, now it is happening that it is possible to achieve this kind of ground state, motional ground state. And I will give you some numbers, what numbers are adequate to test the quantum nature of gravity. Now, a bit of quantum field theory. We know if you want to compute a potential, we can compute the potential at the tree level, and then we can go on to one loop, two loops, and higher loops we can compute. All that we have to know is to know the propagator. So in this particular example, we need a graviton propagator. So I'm not going into the details of S matrix and computing the non-relativistic potential, but it's just to remind that such machinery exists, and we can calculate the potential. And people have computed this kind of potentials, the Newtonian potential, post-Newtonian corrections. Here I have given only terms which are of the order of 1/c⁴ maximum, but now we know that there are many, many techniques where people can use to compute 1/c⁴ terms. So very higher order terms people can compute via this interaction between matter and gravity by quantizing matter and by quantizing gravity. So now the question is, can we now witness entanglement due to all these terms or not? And for the purpose of the experiment, the first term, the Newton's potential, which was discovered purely by classical understanding of gravity. But in a quantum mechanics, in a quantum world, even the Newtonian potential arises because of quantum nature of gravitational interaction with matter. And this is the term which we can actually test it in a laboratory. Now, in 2017, this is what we suggested, that if you take nanoparticle, so nanoparticle means nanoparticle with, say, a nanodiamond. If you take a mass of nanodiamond of 10⁻⁴, 10⁻⁵ kilogram, and if you create a superposition of size something like 10 micron superposition, then you can actually test the space-time, the nature of space-time, just this gravitational interaction due to gravity purely. How? Now, this is something which now I will discuss. So on your left-hand side, you can see that you have created a macroscopic superposition of two systems of spin. So here we have got spins, and they're separated by a screen. And as we know that electromagnetic interactions can be screened. It's a long-range interaction which we are looking for. So electromagnetic interactions can be screened because you can use a concept of a Faraday cage, but gravity can never be screened. So the two quantum systems can interact through gravitationally, and if gravity is quantum, you would see that there is an entanglement, and as a consequence of the entanglement, what's happening here, the way you are ensuring that, again, is by building the correlation. There is a spin embedded in the system, so you will see after the end of your experiment, so it is an interference experiment, how many times you get spin up, up, up, up, down, down, up, and how many times you get all these combinations. Here, for simplicity, I have just done up, down, but what I mean here is that you build correlation in the x direction, y direction, z directions of your Pauli matrix, sigma, and then then understand whether the two systems are correlated or not. And if they are correlated, then you can establish this entanglement due to purely gravity. So what is important is the witness and this correlation which I was talking about. So there are many witnesses you can construct. When we wrote this paper in 2017, we gave the witness due to Bell, but our colleagues have given better witness, and now we use that witness for our all our papers, including our theory and experimental papers. So this witness is created by colleagues Kim and his students, and is known as the positive partial trace witness, PPT witness. Originally, this PPT witness was given by Hordecki and his colleagues way back in 80s, and this is the witness which we use. What it tells you that for a bipartite system, so bipartite system is a spin up and down system, this witness W can actually witness the entangled state. If there is an entanglement, if there's genuine entanglement, if the trace of W rho is less than 0, you can say that there are states which are entangled states. Now, in experiment, computing the entanglement entropy, like von Neumann's entanglement entropy, and constructing the von Neumann entanglement entropy is extremely costly. And it's impossible because of the effect of decoherence, because there's always the system's coherence can get lost because of its environment. So usually in quantum experiments, people like to work with a witness. So what are the numbers? So this protocol with massive qubits, actually, so you have a massive system, and you have a spin which is embedded in the system. And you can show that the system of left-hand side, Alice and Bob, system 1 and system 2, if they interact purely through gravity, then they get entangled, and the entanglement phase is given by this phase phi 1 and phi 2. E to the power I phi is a global phase which affects both the systems, but what we are interested in is this entanglement phase, and that entanglement phase, you see, it goes as your action divided by h bar. In your action, you have a gravitational potential because it's a non-relativistic regime we are talking about. You can add corrections due to momentum-dependent terms, and they are very small, actually, in a non-relativistic system. So the dominant term is governed by g divided by h bar. Now, g is a small entity, h bar is a small entity, but the rest of the terms, such as mass, the distance d separated, superposition size, delta x, and the time at which you are maintaining this experiment, you can go to a sweet spot where you can make this entanglement phase of the order of 1. And for what range of parameters it becomes order 1? They become order 1 for mass 10 to minus 14 kilogram, superposition size of 100 micron, the d separation is 500 micron, and if you keep this coherence of the system for roughly 1 second, then you can reach the entanglement phase roughly of the order of 1. But as I said, that in a system, in a quantum system, maintaining the coherence is extremely hard. Anything can destroy the coherence of the system. And the whole idea is that if you want to understand the gravity, because the gravitational interaction is so weak, any other interaction will dominate. Electromagnetic interactions will dominate, dipole-dipole interaction will dominate, quadrupole interactions will dominate. So there are many other higher order terms which will dominate, and the idea or the art is to get rid of those electromagnetic interactions. You cannot get rid of it completely, but you can, as an experimentalist, you can mitigate those interactions. And that's why the concept of this Faraday cage comes in, which you need to employ. But besides that, there are other kinds of interactions which can ruin the coherence of your system. Maybe the spin gets decohered because of the impurity of your material. So there are, even if you take nanodiamond may have some other kind of impurities which can destroy the coherence of your system, and that will lead to no experiment at all. So continuously in a quantum technology, people are trying to enhance the coherence of these quantum objects, and the idea is that maybe in 5 years, 10 years, we have enough coherence so that we can maintain the experiment for 1 second and perform and do the test for this beautiful experiment. So as I said, that the decoherence is the biggest challenge, and you can see in one of the plots the witness and the gamma is the decoherence parameter, and depending on these two, you can see that how large superposition has to be delta x for a separation of roughly 35 microns. So the distance d, which I was talking about a few minutes ago, something like 500 micron, you don't need exactly 500 micron. You can actually make it, even shrink it by clever design, and that clever design requires some amount of ingenuity, as I said, to get rid of the electromagnetic interaction due to Faraday cage and so on and so forth. So one of the tasks is, I will not bore you with the numbers, but I wanted to emphasize that it is a statistical experiment. It's exactly like your LHC. You cannot just decide it in just one experiment. You have to repeat the experiment, because the number of repetition increases by the decoherence. Because in any experiment run to run, the decoherence may not be exactly the same, and as a consequence, if the decoherence parameter changes, your number of runs increases. So just to give an example, if you want to ensure that this witness is negative, that's what you require to test the quantum nature of gravity. For 2-qubit system, you would require many runs for a witness, for a decoherence parameter such as 0.1. So this is your 0.1, the blue line. You see that to get 99.99% confidence level, you would need something like 35,000 runs. And if every experiment takes 1 second to run, then 35,000 times 1 second can tell you some number, which is roughly of the order of 6 months or so, with all the maintenance and all. It can be, you may have to run the experiment for years to ascertain whether gravity is quantum or not in this kind of experiment. So maintaining the quantum coherence is one of the biggest challenge for us. Certain technology exists. So people have recently managed to cool it down, macroscopic system, to the motional ground state in Zurich and in Vienna. The pressure we need to maintain this system for coherence up to 1 second is amazing pressure. It's 10⁻13 Pascal, but such kind of pressures exist in a collider, in LHC collider, when you collide the two proton beams. So in the tube, the vacuum is as good as 10⁻13 Pascal. If there is a small change in the pressure, the collision of the protons will not happen, and as a consequence, you will lose the event rates. So such technologies do exist already to get such a high level of pressure in CERN. You need to make sure that the ambient temperature is very around 4 Kelvin or even below 4 Kelvin, and you need to take this entire experiment and put it in a chamber such as vibrational isolation. This is a similar chamber which people use in the context of LIGO experiment or Virgo experiment or Einstein telescope experiment, because it's a 1 Hertz experiment. So you need to get rid of the noise all the way beyond 1 Hertz. So you need to do all these things to make sure to achieve the quantum coherence of the system. And this is a prototype of the experiment where you can see a small nanodiamond is being levitated in a vacuum in presence of 2 magnets, the needle-shaped magnets, which are 3 millimeter magnets. But now this is the old technology. What we are trying to achieve is that we want to levitate a nanodiamond and perform the experiment in a chip. In a chip, how big is the chip? The chip is very, very tiny. The chip is something like a millimeter-sized chip, where you see that your nanodiamond is levitated, and the currents which have the wires is a wire-carrying chip, and it kind of this configuration levitates the diamond, because diamond is a diamagnetic object. It's called diamagnetic levitation, and then you have to make sure that the Casimir polar potential, because the diamond is a dielectric medium, so the screen is a conductor, so there is a Casimir between dielectric systems such as nanodiamond and your screen. So Casimir polar is there, dipole interaction is there, magnetic dipoles interactions there, and then eventually there is a gravity. And you can see in this plot is the potential and the distance away. Z0 is the distance away from the screen, and you see that at some point gravity starts dominating. So this is the place where you can hope to do an experiment, roughly around 10⁻⁴ meter. So this is what we are trying to do. This experiment is about, as I said, we are playing with the nitrogen vacancy centered, NV-centered nanodiamond. Partly because this is a very useful quantum system. It can act like a qubit, because what happens is that diamond is a carbon, but you can create a defect inside this diamond, which is called nitrogen vacancy, and there you can implant electron. So electron becomes your qubit system, but now this electron is being hosted by diamond, and diamond is a heavy system, so it's a massive qubit. Right now, the coherence of such qubits is around milliseconds, but you can improve the coherence by many folds, actually. And people are trying to even do various quantum technologies to increase the coherence of such a system beyond 1 second. And groups in Delft in Netherlands, they have actually, by mapping the electronic spin into the nuclear spin, exactly like your hyperfine splitting in hydrogen atom, where your spin, nuclear spin, electron spin can be up, or nuclear spin, electron spin can be down, up and down state. And so this way it becomes a spin neutral system. But in the spin neutral system, you can maintain the quantum coherence. You can map the quantum information to the nuclear spin and enhance the coherence of the system even beyond 1 second. So such quantum technologies are becoming available for us. So that is very nice. And at the end of the day, the way you want to create the superposition is through Stern-Gerlach setup. So you let the system go through inhomogeneous magnetic field as I have shown here, by the two trajectories, the spin up and spin down will see different force, and as a consequence of the different force, you create a tiny superposition. And this is the superposition which we want to now understand and create it in this in the chip. On top of the chip, you want to create a macroscopic superposition, something of the order of 10 micron, 20 micron, to perform the experiment. Now, as I can see that my time is running up, and I don't want to take, because for the next speaker, I don't want to take much time. So I just want to give you an example that a prototype experiment has been done, which I have been involved as a theorist by a group from Israel, Ron Folman, with atoms. Now, with the atoms, this interferometer experiment, the one which I was explaining to you, the Stern-Gerlach experiment, has been performed. One loop experiment has been performed, which is, in the case of atoms, the mass is 10 to the minus 26 kilogram with the rubidium, 10 to the 4 rubidium atoms. But now we want to go from 10 to the minus 26 kilograms all the way to 10 to the minus 14 kilogram, which is roughly, you can see that a huge jump. 15 orders of 12 orders of magnitude jump we need to do. So gradually we are trying to increase the mass. So 10 to the minus 26 kilogram to 10 to the minus 20 kilogram, 21 kilogram, and then eventually going to 10 to the minus 14 kilogram to perform superposition size of 10 microns and so 20 microns to perform the experiment. It's a long shot experiment. I hope that within 10 years, 15 years time, eventually we'll be able to do the experiment. But in the 5 years time, we are hoping that we can take this massive nanoparticle, nanodiamond, and we can create a superposition size roughly of the order of nanometers. And from there, we push the technology all the way to see whether we can perform the experiment required for gravity. So I did not get much time to talk about. You see that you can. I just hopefully I have given you the glimpse that quantum gravity meets quantum information, quantum technology. But there's a huge amount of particle physics involved, because also you can test physics beyond the standard model. If you can test gravity, you can also test perhaps axion physics or fifth force, because they can also, if they are quantum in nature, then they will entangle and they will imprint their entanglement into their phase. And you can see new physics coming from these tabletop experiments. There's a huge amount of condensed matter, because the material, the choice of the material, the surface of the material, everything is governed, the coherence of the spin, they're all governed by the properties of the material science and the condensed matter aspects of the system. The laser physics, because we want to manipulate the state, so we need to understand the laser properties extremely well. And trust me, you need to even protect the experiment from astrophysical sources like cosmic rays and all sorts of seismic vibrations and things like that. So it connects every branch of physics. So this is a very interesting thing, that is, if you want to understand very simple question like whether space-time is classical or quantum, it leads to understanding of the entire gamut of your undergraduate level physics or graduate level physics. And so this is a highly disruptive technology to create two systems at once, and to test the nature of gravity. It reminds you of this famous Star Trek story where the captain would tell to the engineer, "Scotty, beam me up." And so that's the kind of disruptive technology we want to create, but we want to create the coherent system. And it's highly ambitious in nature, but nevertheless, this is what it requires to do such bold experiments to test the quantum nature of gravity. So it's a community effort. Please join us. You can always contact me if you are interested in joining this collaboration. And it's a 20 years old program for us. So right now we are at the stage where we want to create this superposition size, a very tiny superposition size, something of the order of 10 to the minus 15 meter, 10 to the minus 12 meter, 10 to the minus 8 meter, for a mass of 10 to the minus 15 kilograms. So in 10 years time, we want to achieve this. And then in 10 to 20 years time, we really want to push our ambitions and go for a superposition size, roughly of the order of a micron with to 100 micron, to really test the quantum nature of gravity. And throughout this trajectory, actually, we are always in the discovery potential, because as I said, that maybe and the end stage will be to test the quantum nature of gravity, but in between you can test physics beyond the Standard Model, because that will be your new background. So I hope that with this, I would like to thank all of you, because I know that my time is running out, and I thank you for your patience, and I'm really sorry that for the first few slides you could not see. Thanks. Thank you.
Thank you so much, Professor. We are also sorry about not letting you know about the technical problem, but I believe everyone enjoyed your presentation. Okay, so the next one, we are honored to welcome Professor Dr. Itzhak Bars from the University of Southern California. The title of his talk will be "The Higgs Fields Govern the Interior of Black Holes." Can you hear us, sir?
I can hear you. Can you?
Yes, we can.
Okay.
Thank you. So the floor is yours.
All right. Thank you. So I will be talking about some new physics involving the Higgs field and black holes. But before I begin, I want to express my deep gratitude to Feza Gürsey for playing a pivotal role in my journey to become a physicist. I met Feza in 1965 at Robert College, which later became Boğaziçi University, when I was a sophomore majoring in electrical engineering. He was then a famous physicist that was visiting briefly to give a lecture. And he graciously chatted with students like me that had a strong interest in physics. That fortunate encounter proved to be life-changing for me. A single conversation with Feza illuminated a path I hadn't fully seen before, a path towards a research career in physics. A year later, I changed my major to physics at Robert College, and in 1967, I began my PhD studies at Yale University. As luck would have it, Feza joined as a professor in 1968, just as I was selecting a doctoral advisor. Under his guidance, I completed my PhD in 1971. My thesis focused on how to incorporate spin and flavors of quarks in the Veneziano model, a topic that no one else at Yale was working on at that time. Feza, with his far-reaching vision, encouraged me to pursue it, granting me the freedom to develop independently. After 2 years as a postdoc at Berkeley, while I was in my second year as an assistant professor at Stanford in 1975, I was invited to return to Yale as a faculty member. There, I had the privilege of working alongside Feza as a colleague for the next decade. During this period, Suhanem and Feza made us feel like family, like me, many other students and friends that we used to see at his home very often. I will always be grateful to him, not only for his mentorship, but also for inspiring in me a deep appreciation for the role of symmetry in physics. It is a true honor to participate in this workshop dedicated to his memory. My sincere thanks to organizers for inviting me. Thank you. So now I go on with my talk. It's about new physics horizons that is spearheaded by the Higgs field. So the general takeaway that I hope you will remember are the following general ideas. First, the Higgs field is best known as a small local fluctuation. This is for the Higgs particle, a small local fluctuation, on top of a big universal constant vacuum expectation value of about 246 GeV that fills the entire universe like a calm ocean. And the Higgs particle is like a small fluctuation on top of this calm ocean. And this calm ocean provides the source of mass to all particles. So that's an extremely important role for the Higgs. But it seems like a kind of a boring one. It is just calm most of the time. So is that all there is to the Higgs? And I claim there is a lot more. So the Higgs field is considerably more influential in shaping the universe in other ways that are unknown up to now. And I'm making the following claims: that it is a non-perturbative, space-time dependent field, not just constant, space-time dependent field, in all regions of strong gravity, wherever there is strong gravity. We are observing the Higgs now in weak gravity. At low energy physics, where there is strong gravity, there will always also be high energy physics. And so that's an area that has not been explored yet. And I'm claiming that it is a strongly space-time dependent field in all regions where there is strong gravity. And in those regions, it has a dramatic and very wild behavior. For example, in the interiors of black holes, and also at the Big Bang cosmology, at the very early part of the cosmology, and also before the Big Bang. So the Higgs field in such regions, it creates new regions of space-time behind singularities, behind the black hole singularity, behind the Big Bang singularity, where there is anti-gravity. Anti-gravity meaning repulsive gravity rather than attractive gravity. So there are new regions created by the Higgs field. And then the regions of gravity, together with the anti-gravity regions, they form a geodesically complete spacetime, which is missing in the standard theory of particle physics coupled to general relativity, and also in its generalizations of string theory. So it also therefore provides, the Higgs field provides gravity plus anti-gravity regions together, that they form geodesically complete spacetime, which is very important, something missing in fundamental theory. Okay, so these are the general things. So now I will begin with the problem of geodesic incompleteness in the standard theory. So the standard model, together with general relativity, they are very successful phenomenologically, but they have a fundamental problem, besides the fact that it is not renormalizable, but that's a different issue. It has to do with quantum gravity. But this is even before talking about quantum gravity. There is a fundamental problem, which is this geodesic incompleteness. So let me describe a little bit of what that is. It has to do with an example, such as a particle that is falling into a black hole, and it reaches the singularity in a finite amount of proper time. And once it reaches there, it doesn't know what to do, because the theory doesn't know what to do. And the theory stops describing the physics and what phenomena can happen. So this is the incompleteness of the theory. So this is a picture describing what it is. And I want to distinguish what I mean here by proper time versus the static observer's time. So an observer which is outside of the black hole uses what is called a clock that ticks with a t, whereas the infalling observer, the particle itself, has its own time called the proper time. And so the outside observer's time, t, is a function of the proper time. And then the observer knows that it passes through the horizon and it reaches the singularity in a finite amount of time, of proper time, and then doesn't know what to do, because the theory, the standard theory, doesn't say what is going to happen there. So in a more complete way of describing the space-time of what goes on, rather than using position r, distance r, and t, r meaning just distance to the center of the black hole, instead of using r and t, meaning this t, there is a Kruskal-Sekeres coordinates space-time that is more complete as compared to the r and t space-time. And in this space-time, you can see that only part of the u-v space, u and v can go all the way to infinity. It's only a partial amount of this space-time that is considered to be physical in black hole physics. So a massless particle that is created outside of the black hole. These lines here represent the horizon of the black hole. So a particle that's starting in region 1 outside of the black hole passes to the horizon and then reaches the singularity, just as it's reaching the singularity in the RT coordinate system. And there that it hits the singularity, which is this wavy line, and doesn't know what to do there. Continue, reflect, do what? It's not being guided by the present theory. So the standard model coupled to general relativity gives no clues about what happens at the next instant of proper time. So this is a problem. It has been a problem, of course, from the very beginning of understanding black holes. And usually this is ignored, and it is relayed. The question is relayed to what happens to quantum gravity, which eventually is supposed to tell us what actually is supposed to happen at the black hole, at singularities, or maybe even, according to some approaches, that there may not be a singularity. Now, actually, string theory and other models of quantum gravity suffer from the same problem, especially when they are described in terms of some geometry, such as background fields, that are also geodesically incomplete. But there are some approaches that are non-geometric in string theory that suggest that the black hole singularity may not exist, but these are just toy models. They are not complete theories like the standard model coupled to general relativity. It doesn't come anywhere close as being a complete theory. So and also there are plenty of open problems in such approaches in string theory. So it is not really convincing about what actually happens there. But I suggest there is actually a solution independent of whether it is quantum or classical relativity, that there is a cure to the geodesic incompleteness, and that cure goes through local scale invariance, but in a very special form. Which kind of scale invariance we are talking about? We are talking about taking the degrees of freedom in the coupled standard model and general relativity, a rescaling, a local rescaling, omega is a function of x, that is rescaling the metric as well as the Higgs and any other scalar field by the inverse. This is squared, this is omega to the -1, fermions with -3/2, and gauge bosons vectors such as photon, gluons, and so on, not scaling at all. So the theory can be made to be locally scale invariant under such rescalings. So that theory, I'm calling it the improved standard model plus general relativity, which also leads to an similarly improved string theory. So here is the Lagrangian of this theory, which is very similar. It's basically very similar to the standard model, including the Higgs doublet. And then it includes an additional scalar field phi, which is a singlet under SU2 cos U1. So this is the Lagrangian. I'm going to describe it in a little bit more detail about the important aspects of it. It was in a more complete way in this form. It was discussed in 2014 by me and collaborators, but it was really derived initially from what I call two-time physics, much earlier. And then this transformation, this local transformation, is actually a relic symmetry from 4+2 dimensions, 4 space and 2 time dimensions, where the transformation omega is just a mixing of the extra space and extra time dimensions together with the usual 3 space and 1 time dimensions. So, but in the standard model in 3+1 dimensions, although it is derived from 4+2 dimensions, it's a gauge choice. It comes down to 3+1 dimensions. And in 3+1 dimensions, it comes with a local scale invariance, which is what I'm talking about, which originally is really, it has to do with the presence of an extra time and an extra space dimensions. So it is much deeper than just the local scale symmetry that was initially introduced by Weil. So in this form, the theory requires gravity to be there. This is apparent from this fixed coefficient 1/12, which is the coupling of scalars, how scalars couple to the curvature of space-time. So this cannot be changed because of this local scale symmetry, the coefficient 1/12. It is because all scalars must be conformally coupled, and conformally coupled scalars come with this very special coefficient 1/12 in relation to when the scalars are originating in their kinetic term with this 1/2 in front of it. Okay, so gravity is required in this form. It cannot be ignored. And then the special form of the Weyl symmetry here means that there is no Weyl gauge field introduced. Originally, Weyl needed a gauge field that was the main aspect, the main new degree of freedom. Here, there is no new degree of freedom except for this phi. And then the special form is that there is this relative minus sign in the kinetic term and also in the way that they couple, these two scalars couple to the curvature. So this is the special form. And this special form is really the gate, okay? This relative minus sign is the gate to new physics. This is where it's going to come from. And that's what I'm going to focus on in the rest. So now this theory is geodesically complete. I'm going to describe how. It improves the standard model in the vicinity of singularities, and it tells you how it is that there is new information when you reach the singularity and what to do. What is it that the particles or degrees of freedom that reach the singularity, what is it that they must do? Okay, so this is what we learn in this geodesically complete version of the theory. Now, but at low energies, as far as the physics that we observe at low energies and far from singularities, this improved theory is as accurate as the usual standard model and general relativity in fitting all non-phenomenology in those regions, in the familiar regions. So it is as good a theory phenomenologically with everything that we have observed so far in physics, but now we have new opportunities, new gates of information for new physics that is coming because of the differences that exist between the improved theory and the usual theory. So this was the Lagrangian I showed you. So this part of
You'll need to unlock your iPhone first.
So this part of the Lagrangian is the same as the usual standard model, so no changes from that. And then the presence of the Higgs field, also no changes from that. The new things is the presence of this extra scalar, and also this things that I'm going to emphasize that are the new things. Okay, so this part with the relative minus sign. So in this term in the usual theory is what is called the Einstein-Hilbert term. So this thing that I encircled, the parenthesis, is really the Newton constant or the gravitational constant multiplying r. R is the curvature. So this is in the usual theory. Whereas in this theory, in this improved theory, it is a function. This is a function that depends on the fields. It's a dynamical gravitational strength. It can change depending on the position. And then it can also change sign, which is the crucial thing that I'm going to talk about. So the other thing that is different is that the potential that involves both of these fields is more general than just being the quartic potential in the standard model Lagrangian. I will come to that, but let me keep it open for now. But the more general form is that I can pull because this form, this V, is a homogeneous function of degree 4. So namely, when you make the transformation with the local scale symmetry, when you make a transformation on phi and h, you just get back the same potential, except for this overall factor of omega to the minus 4. So this is a homogeneous function of its arguments phi and h. So therefore, I can pull phi to the fourth, to the front, because of this homogeneous of degree 4. And then what remains is put it to the front, and then what remains is a function which is a ratio of h over phi. So therefore, any function v, which is a function of this ratio that I'm calling it little h, any function of v is possible as far as this local scale symmetry is concerned. So a more general v is allowed. Although I'm not going, for this lecture, I'm not going to use that, but eventually it is important that it is there. Okay, so now let's talk about the low energy physics of this full theory. And the low energy physics corresponds to the fact when phi is of order 10 to the 19 GeV. This is the Planck scale. And then the Higgs field is of order 246 GeV. So in the plot of the Higgs field on the vertical axis and phi on the horizontal axis, it is in the neighborhood of this point. So namely very small h, very small Higgs field as compared to phi, which is very, very large. So it is this neighborhood in field space, in the scalar field space, it is the neighborhood of this point that corresponds to the low energy regime that we observe up to all the most powerful accelerators that we have. So this is the regime that is explored in this theory. But this regime, low energy regime, can be captured with a gauge choice in this theory. The gauge choice that is because of this local scale symmetry. I can therefore, by a local scale transformation, I can make phi to just be a constant that I will call phi 0, where phi 0 is 10 to the 19 GeV. In that case, this ratio that I talked about here, 246 divided by 10 to the 19 squared, it is 10 to the minus 33, which means h is a very tiny thing in this potential. And also in this expression of the dynamical gravitational strength, this term is much, much smaller as compared to the phi. So therefore, this dynamical strength is basically a constant. And so this gives the usual gravitational strength that you see in low energy physics. And then once we are in that regime, and once I am in this gauge, so therefore I have a tiny h, and then without going into the details, you can reproduce, I have a new scale, okay, this scale that has been introduced by a gauge choice, and then this scale just through the potential generates all the other scales that are important at low energy physics, including the Newton constant, including the cosmological constant, including the vacuum value of the Higgs, and including the mass of the Higgs particle. So therefore, all dimension full parameters in the usual standard model, they emerge from the single dimension full source, which is phi 0. This is a very attractive feature about the origin of mass. So namely, the origin of mass goes back to this phi 0 as observed in low energy physics. So this is a very attractive feature to put together all of these dimension full parameters as big as coming only from this gauge choice, phi 0. So the improved standard model is the same, basically the same as the usual standard model at low energies, and therefore it is a correct, physically, phenomenologically correct for all non-phenomenology at low energies and in weak gravity. So this establishes that the improved standard model is just as good as the usual standard model in the regimes where it has been actually observed and measured. All right, so now what about the differences between the two? And as I already emphasized, the differences come from this term and also from that term. So let's try to explore where we go with those differences. When I explore not only that very tiny regime that was a single point in this plot of the Higgs that I'm calling S now, the Higgs versus phi, that was a very tiny spot. When I explore the entire space of the scalar fields in this theory. So when I do that, let's take a look. So this term, which was a dynamical strength, I can rewrite it by pulling out phi squared. And then what I have is 1 minus h squared. H was this little h squared here. And then h, remember, was a very tiny term in low energies. But if you look here, h, first of all, it is scale invariant because the scale transformations on h and phi, they cancel each other. And little h is scale invariant, so it's independent. Whatever I'm about to say about h is independent of choosing any kind of gauge. It is true in all possible gauges that you can imagine. So if you look here, you can see that this scale invariant factor, it can vanish if h is large, not tiny, but if it is large of order 1, it can vanish. And it can also become also negative. So when it is positive, okay, when h squared is smaller than 1, so in this plot here, S is h, okay? S is h. So in this plot, if you look at these dotted lines, the diagonal dotted lines, the regime in which phi is larger than s, that's when h squared is smaller than 1. So that in that regime, the gravitational strength is positive. Okay, so in that regime it is positive. So I will call that the gravity regime. The gravity, namely usual attractive gravity, namely the sign of the gravitational constant being positive. So this is gravitational regime, and also this is the gravitational regime when the absolute value of phi is larger than s. And when h squared is larger than 1, then the gravitational strength is negative. So this is therefore the regime in which s, which is the Higgs, when the Higgs is larger than phi. So this is the blue sides. It is the anti-gravity regime. So this theory is predicting that there is additional space-time, there is additional region of spacetimes in which gravity is going to be negative. It's going to be repulsive, and these two regions are joined together when h becomes 1. And then I am about to tell you that when h becomes 1, these dotted lines is where there are singularities of gravity, such as black holes. So, but the first thing is that this theory is predicting that there are additional space-time regions where gravity is going to be repulsive, and then that the two regions, they come on opposite sides of singularities, which is the dotted lines. So now what happens when h becomes 1? So we look at the equations of motion, in particular, the Einstein equations of motion that come from minimizing this action with respect to the metric. So on the left side, you have the geometry. On the right side, you have the energy momentum tensor. And the energy momentum tensor that emerges in this theory has in it 1 over this factor. Okay, 1 over this factor, or 12 over the inverse, in other words, of this factor. So, so this factor was just a constant in the usual theory, in the standard model. It's an overall constant. There is nothing that happens because when it is a constant. But in this case, it can vanish in the denominator. Okay, the denominator can vanish. So therefore, there is a singularity in this equation. But the right-hand side becomes infinite. Then the left-hand side, which is the geometry, it develops a singularity, such as a black hole, as well as other gravitational singularities. So this is exactly when this is 0, is exactly when s squared is equal to phi squared, when the Higgs squared is equal to phi squared, which is the dotted lines. So therefore, the gravity and anti-gravity regions, as predicted in this theory, they are separated from one another by gravitational singularities. We are on one side, okay? We live on one side of this graph. So we are at a single little point, very far away from singularities. But the theory predicts that there can be phenomena in which the field strengths, the Higgs versus the phi, they can be very different than what we are observing currently, and that we can reach singularities and even cross singularities to the other side into new spacetimes where there is anti-gravity. So now, what about the other unknown, v of h? I said it can be any function. However, when h is very, very small, so namely when we are at that regime of low energy physics, we know the form of this v of h. It is the quartic potential. And when we have the quartic potential, the unknown function is actually determined. We know what that function is. And that function, as I said, tells us where the Higgs vacuum comes from, which equals to this parameter alpha, and where dark energy comes from, which has to do with this number, lambda prime, a very tiny, small thing. So v of h is known when we are far away from singularities, when we are in weak gravity. So I'm going to use this information in order to understand the physics of a black hole. So now let's go to that. All right, so here we are, what I just said. And I want to parameterize these two regions, the space-time of these two regions, and in a way that helps me to understand singularities and black holes. All right, so now, first of all, which region are we, in the red or in the blue? So that the Higgs determines that, right? So as we said, when the Higgs is larger than phi, then we are in the blue region. So we have a space-time that has its own time and space as measured from the black hole, okay, namely from the dotted line. From the black hole, we are in the blue region when the Higgs is larger, and we are in the blue region, in the gravity region, when the Higgs is small, okay, when the Higgs is small relative to the Planck scale. So, so we have two separate space-times in order to describe what the physics is. But I'm going to join them together. I will find a way of putting them together in a way that will help me understand black holes, what happens at that intermediate region. So the complete space-time put together, I'm going to use the same symbol, R and T, rather than T and R and T tilde and R. I'm going to use the same T and R for both. But I will define R, namely, that is the distance to the black hole, the distance to the origin, that R. I'm going to define it as the distance, as the usual, this is a vector, and then the distance is the magnitude of the vector, R, multiplied by the sine of 1 minus h squared. That was, remember, gauge invariant, scale invariant. So multiplied by that sign, I will define little r to mean that. So namely distance, which is positive from the black hole, whether I am in the blue region or whether I am in the red region, but multiplied by this sign that tells me whether I am on the blue side or on the gravity side. So namely, I am defining a symbol r that can be both negative and positive. The usual r is always, of course, positive. But in this definition, positive r means I am in the gravity region. Negative r little r means that I am in the anti-gravity region. So I'm putting them together as a single parameterization r and t, but with little r being defined like this. So namely, we have correlated signs that when the sign of h squared, 1 minus h squared, is positive or negative, that corresponds to the sign of r. So now if we come to the Kruskal-Sekeres diagram and go back to the trajectory of a massless particle that goes and hits the black hole, what happens there? So now what happens is that now we have a blue region opened up behind the singularity. Previously, it was not possible, but now the negative region of R, when R is negative, corresponds in this UV diagram, corresponds to these blue regions 5 and 6. Okay, so this is the black hole, the interior of the black hole, behind the singularity, the interior of the black hole behind the singularity, and this is the interior of the white hole behind the white hole singularity. So what happens to a massless particle that comes and reaches there, and it was geodesically incomplete when that region, we didn't know whether it was there or not, and there was no guidance from the usual standard model, but now the improved standard model tells us that there is such a region, and so for R positive, we are in the regions, the traditional regions 1, 2, 3, 4 of a black hole, and then when R is negative, we are in these anti-gravity regions. So which are now physical. They are physical because I'm saying there is anti-gravity, and I'm giving you a theory that is going to tell me exactly what does happen in those regions. So here is what happens. I can now do my computations of computing R as a function of proper time and T as a function of proper time. I allow R to be from minus infinity to plus infinity. In my new way of computing the geodesics, I compute the geodesics for a massless particle, and I find that it can go through the singularity to the other side. It reaches to behind the singularity of a black hole, or it can get reflected. It just depends on the dependence on the proper time when I solve these equations. So these are the blue and the red trajectories. So the only thing that was easy here was just that I allowed R to be negative. But now I'm going to tell you some more about the properties of the physics properties that exist in the anti-gravity region. All right, so not only that the geometry, which is the metric G mu nu, is being completed to be a new geodesically complete metric, but also the field space, the scalar field space, is also being completed by allowing phi and h, the Higgs, and also the metric, which is the geometry, to exist in all the regions that are defined by the theory, that are predicted by the theory. Okay, so look, what happening is that local scale invariance does not remove the singularity. It is there, but it does prescribe how it traverses it and how to complete the space-time. So this is the first thing about what local scale invariance does, but in the special form of local scale invariance that I described. Okay, so now let me go back to the equations of motion, and then from there try to figure out details of what goes on in the anti-gravity regions, in the new regions. The Higgs here, which was a doublet, I'm going to take it in the what we call the unitary gauge with respect to the SU2 cross U1. So it is S, this S that I'm describing here. It is just the Higgs field in the unitary gauge. So in that unitary gauge, I'm going to look at the equations of motions derived there, and I'm look for solutions in which the scalar fields are going to be constants. So I'm going to drop all the derivatives in my equations of motion, and I will go far away from singularities in the asymptotic regions of the gravity region, as well as its asymptotic regions of the anti-gravity region, so namely far away from the singularities. I will search from solutions of the equations of motion asymptotically far away from singularities in the weak gravity regime. So in the weak gravity regime, I know the potential, which is the standard model potential, the quartic standard model potential. So I will go with that, and then just look at the equations of motion. So this is like the analog of what used to be done, minimizing just the potential. So when you remove all the derivatives, you just minimize the potential in looking at the equations of motion, except that now there is something else. If I allow to be in a space-time in which there is curvature, and there will be curvature, because this potential is going to give me a cosmological constant. Because there is a cosmological constant, there will be a curvature. So because there is a curvature, this term also contributes to the equations of motion when I minimize with respect to the scalars, phi or h. So I get equations of motion of only scalars. I'm searching only for scalars, constants. But in these equations, there is a new term, I'm not minimizing just v by itself. I'm minimizing v plus this, where r is a constant. So I have these additional terms. So therefore, when r is a constant, I'm searching from these two equations for what phi is and what s is. All right, so in the gravity patch, I get solutions that I will call phi plus and s plus. In the anti-gravity patch, I will call them phi minus and s minus. And then for phi plus and s plus, what appears here, okay, is just the gravitational constant. That combination is the gravitational constant in the gravity regime. So I identify that with the Newton constant. And then the phi minus s minus, which is in that regime, again, that combination, I will call it anti-gravity constant. So therefore, it is it's not the Newton constant. I will call it G tilde. And it is negative. This combination is negative because we are in anti-gravity. And then the cosmological constant that emerges from V, from this term, actually, it turns out that the cosmological constants are lambda plus lambda minus. It is V evaluated either in the plus region or in the minus region once I give you the solutions. And so this defines the gravitational strengths in one region and the other. So they are just constants because I'm looking for constant solutions. And then once I do that, then I end up determining also, because I have a cosmological constant, I also end up determining also that R is something, the curvature is something. And then what you find is that in the positive regime, the curvature is proportional to this lambda prime, okay, to this lambda prime, which is tiny, a very small positive curvature, so which says that we live in de Sitter space. And then in the negative regime, you find R, which is proportional to that constant, lambda, but divided by this G tilde. G tilde, we don't know what it is. This G is the Newton constant. We know what it is. And lambda prime is very tiny because the cosmological constant, which is proportional to lambda prime, is extremely tiny in where we live. So R plus is a very small curvature, de Sitter curvature. For the negative side, we don't know, because we don't know what G tilde is. It's the only unknown in what I'm going to say, but it is proportional to lambda. Then what? So if G tilde is very small, namely very weak gravity, then R minus is huge because lambda is of order 1. So then R minus is huge if we are in weak gravity, anti-gravity, sorry, and if R minus is very small if we are in very strong anti-gravity. Okay, so we have these additional information that we are learning here. So therefore, the gravity regime, which is we live around a point there. Okay, it is in this field space. We are at that asymptotically. Okay, when R is infinite, far away from singularities, we are in that regime as far as the values of S and phi is concerned. Phi plus and phi minus. Phi plus and S plus. We are in that point that I distinguished before. And for anti-gravity, we are at a point like that in the anti-gravity regime. And here it is anti-de Sitter, because I have negative curvature, but we don't know the strength, and therefore we don't know the strength of the curvature as well. It can be very small, it can be very large. Okay, so now we have this additional information. So, but the gravity and anti-gravity they are connected only at the singularity because they are separated by these dotted lines, where there is a singularity. Therefore, we must have a singular geometry that separates these asymptotic solutions that I have just told you about. There must be a singular geometry that separates them. So I'm going to assume a black hole separates them. So if I have a black hole, if I have a black hole that separates these asymptotic solutions, then I can ask, well, what else can I say about the physics that occurs here? Okay, so now first let me take, rather than being asymptotic, suppose I do the following. Suppose I take in the entire region, I have that constant, that asymptotic constant dominates the entire region in gravity, and the other asymptotic constant, the minuses, dominate the entire, not only asymptotic, but the entire regime. So if I take everywhere within the plus or the minus regions that R and phi and H are constants, the constant that I just mentioned, then you find out that all the equations, including derivatives, all the equations, because they are constants in the entire region, all equations are satisfied everywhere in the gravity and the anti-gravity regime. So I'm solving really solutions everywhere, except that phi and H make a jump. Okay, they make a jump from one side because there is the phi plus phi minus. They make a jump at the singularity at R equal to 0. They make a jump to the other side, which is a different set of constants. So therefore, except at R equal to 0, because there is a jump, derivatives, of course, are going to be delta functions. So therefore, except at R equal to 0, there is a complete solution of the equations of motion of this improved theory. So there remains to understand what happens at R equal to 0, which I will come to. But this is a solution almost everywhere in the combined spacetime when I have a black hole. Okay, when I have a black hole. So when I have a black hole means that I choose the metric in this form, where this factor in the metric contains a singularity 1 over R at R equal to 0. And then the cosmological constants are taken into account through this overall R squared term. So R0 here corresponds to basically the mass of the black hole multiplied by the gravitational constant G. This is the radius. R0 is the radius of the horizon of the black hole, and then lambda, 1/3 over 1/3, is the lambda plus or lambda minus are the cosmological constants that I mentioned in the previous transparency. So now I'm going to just give you some plots of what these things look like. A and A inverse, what they look like. So A, when R is positive, this is the usual, okay, the usual side of a black hole in ds, in the Sitter space. So it has this shape, this general shape. Near R equal to 0, it diverges. That's because of this 1 over R. Then it has a 0. It has a 0 at the R sub H. H stands for the hole, for the black hole. It is the horizon. And it has another 0, second 0 at RC. C stands for the cosmological horizon. So these two zeros of A at RH at RC are the cosmological horizons. And then eventually it goes to minus infinity. That's because of this R squared. As R grows, so with a minus sign, it just goes down. And on the negative side...
I'm sorry for interrupting, but I would like to remind you that the time is almost up.
Okay, all right, then I will accelerate. I'm sorry about that. So anyway, so important here is the product of U and V that I was talking about as a function of R. I will have to jump and just tell you that I can construct for this new black hole that I'm calling it SDS plus SADS. S stands for Schwarzschild ADS and Schwarzschild de Sitter. So the combined Kruskal diagrams are here. What is new is these yellow regions, okay? The yellow regions in 5 and 6. These regions did not exist before. Now it becomes geodesically complete by including these regions. And then there is the Penrose diagram associated with this, which also shows you what is the causal structure. So namely, if we have a particle that is moving in different regions, 1, 2, 3, 4, 5, and so on, in which directions they must move. So namely, these little pictures here tell you in which directions, in which angles they can move. If they are in region 1, in region 2, in region 5, etc. So this tells you the causal structure. If you look at this entire causal structure, then you find out that a particle that falls into the black hole passes through the horizon. It passes through the singularity. It reaches the end of R equals to infinity, the end of the anti-gravity region, which is ADS. ADS geometry works like a mirror, a box that has mirrors in it. And so therefore that one gets deflected like a mirror and then moves on back through the singularity, back through the other horizon into new space-times. So in other words, we learned that there is a complete geodesics, and what happens to information? What happens to information that falls into a black hole? Well, it just goes to new places. It passes through anti-gravity, and it goes to this mirror region that exists for black holes, region 4. So this is what happens to information, and what happens finally to this jump that I was talking about for phi and s at the singularity. It turns out it passes through 0. Okay, so namely, on the positive side, phi and s were some constants. On the negative region, phi and s are some other constants. How do they connect to each other? Passing through the singularity is that they both of them vanish through 0. And this is a remarkable dramatic behavior of the Higgs vanishing at the singularity. Vanishing at the singularity means, so this is what happens in the S phi. Okay, so from minus infinity, it goes through the singularity, the dotted lines, goes on the dotted line tangentially, and then goes into the positive region. So from anti-gravity, it passes tangentially through the singularity, and then goes into the positive region to R equals to infinity. So that's the general behavior. And then passing through the singularity is remarkable, because passing to the singularity when the Higgs vanishes, so that means SU2 cross U1, the electroweak symmetry gets restored at the singularity. Everything becomes massless at the singularity. Quarks, leptons, W bosons, everything becomes massless at the singularity. And by being massless, then they manage, all of them, they manage to go through the singularity. Massless things go through the singularity. Massive things cannot. But massless things can go through the singularity. And this is quite remarkable, that everything, all matter, goes through the singularity. All the information coming from every single degree of freedom in the standard model goes to the singularity. And this is how the information puzzle that has been around for several decades, it gets removed. Okay, there is no information puzzle in this theory. In this improved theory, there is no information puzzle. We know where information goes, or it's predicted where information goes. It needs to be, of course, verified eventually. Thank you. That's it. I'm done.
Thank you so much. So let me just, okay. We thank Professor Itzhak Bars for his invaluable contributions for the Feza Gürsey Commemoration Day, organized in collaboration by Boğaziçi University, Middle East Technical University, and OSTİM Technical University. Thank you so much, Professor, again.
Thank you.
Okay, so our final speaker in this session is Dr. Naim Göksel Karaçaylı from the Ohio State University, and his presentation is titled Bringing the Dark Universe to Light with Lyman Alpha Forest Cosmology.
Okay. Hello, everyone. Can you hear me?
Yes, we can.
Okay, I'm going to share the screen. Let's do this. I think. All right, can you see the slides?
Yes, we can.
All right, let me get started. First of all, I did my PhD at Yale University. I arrived in like about August 2015, and within 2 weeks, I took this photo. This is Feza Gürsey's portrait. You can see this in Yale Physics Building. Back then, I had a very bad phone camera, so that's why it's blurry, but it says Feza Gürsey down there. And later, a few years later, I found another plaque in one of the classrooms. So it's been valuable to have him as an anchor during my PhD there. Okay, let me get to science. I actually have 15 minutes or so. I have to leave immediately, 8:30 my time, I'm sorry. So I'll go a little quick and I'll end when I have to end. Okay, my work essentially focuses on these three open questions in the standard model. We know the dark matter and dark energy exist to some extent. Existence of dark matter, first of all, indicates that our standard particle physics is incomplete. It has to be extended, and we mostly assume it's probably weakly interacting a massive particle, but we actually don't know. Dark energy is, on the other hand, is even less understood. Is it a new field? Is it a property of space-time? We don't really know. The second question we're trying to understand in particle physics is that what is the total mass and mass hierarchy of neutrinos? We know they have mass, but we cannot measure their absolute masses. And third, this is again can be extended, but I'm not going to talk in this presentation, is how did the inflation happen, which is related to highest energy scales, about probably the quantum fluctuations that grow to be our universe, but again, it's not in this talk. So I'm going to lure you in with more neutrinos. I assume this might be appealing to this audience. So neutrinos come in three eigenstates in flavor: electron, muon, and tau. This is this beautiful image here from Razmi. But their mass states are not the same. So the mass eigenstate is a linear combination of these three flavor eigenstates. And the first one, the new one, is the most electronic one, but it's a combination of all three. And this got the Nobel Prize in 2015. We can measure the mass splitting between these eigenstates through neutrino oscillation experiments. The mass splitting between the first and the second state is given by solar experiments, and the third and the first one is given by atmospheric experiments. And if the first one is the new one, the most electronic one is the lightest, you get what is called a normal ordering. And in that case, the total mass of neutrinos can be 0.06 eV, the minimum. And if it is inverted, the minimum is 0.1 eV. But again, we don't know this total mass. Okay, giving that background, what I'm going to talk about is mostly about gravity and actually data analysis. Let me start with the big picture with the Einstein field equations. We have relating the geometry of space-time to energy momentum tensor, right? In this picture, the space-time is a four-dimensional manifold, and everything moves in this banded manifold according to gravity. And that simple relation just creates amazing physical phenomena starting from black holes, gravitational lensing, gravitational waves, and modern cosmology. It's really amazing how diverse a single equation created different phenomena. And my subfield is called limonal forest under modern cosmology. I'm trying to rebrand it as dark forest. I may not even have a lot of time to go into dark forest, limonal forest details, but I'll try to. Okay, just give you a big overview. I will introduce the standard model of cosmology. I'm going to talk about the experiment I'm working on, which is called the Dark Energy Spectroscopic Instrument, DESI for short. I'll call it DESI. It's an experiment, an instrument. I'll introduce what baryon-acoustic oscillations are and what the limonal forest is. And I will present our second data release. This is data release 2, dynamical dark energy results that became a big splash a few months ago. And if I have time, I might be able to touch on the small-scale information we extract with limonal forest and even cross-correlating these things with gravitational lensing. And again, I have to leave immediately after the talk, but you can email me with questions. Okay, the standard model of cosmology is it's a homogeneous universe with density perturbations on top. So in this, first of all, the homogeneous isotropic universe, we have about 70% of the energy content to be dark energy. It's the pressure that pushes the universe out, that expands the universe, that we describe by dark energy. The lambda here symbolizes the cosmological constant. The remaining 30% is we know to be matter, but of that entire thing, 5% of the total, 5% of the entire universe content is only the visible matter. So 25% of the matter content is baryons, that's what we observe. Anything else is dark matter, we don't really directly observe. And our picture of roughly the entire universe is we have some inflation, the initial quantum fluctuation inflation happens. You have plasma that cools down and creates this afterglow after the photons become able to travel through the universe, initial plasma. This is the cosmic microwave background radiation. For a while, there is nothing that emits light. Then the first stars form, and eventually galaxies and planets form, and we have this very clumpy structure. And we enter accelerated expansion stage of the universe at later times. So our standard model explains our universe very well throughout time and as well as all the structures on top. It's not just universe is expanding. So the cosmic microwave background is the signal we observe when the universe is about 375,000 years old. This is the temperature map, temperature fluctuation map from Planck satellite mission. So the red spots are hotter, blue spots are colder. And as you can see, this is not pure noise. It's not like pure TV static. The red points are closer, whereas the blue points are also closer as well. So there's this big blue clump here. There's a big red island here that are nearby. This can be mathematically quantified through what's called the power spectrum. What is important here is that this structure can be very well fit with our description, theoretical model of cosmology. And then we can further propagate this structure, this initial structure, or evolve it over time. Then what we get is when the universe is about 10 gigayears old, we have galaxies. This is a galaxy map from DESI, and these initial structures grow to form this cosmic web-like structure where you have galaxies of cluster here and gaps in between. So let me talk a little bit of DESI. Dark Energy Spectroscopic Instrument. It is a stage 4. Stage 4 is a funding agency classification. Ground-based, which means it's on Earth, it's not a satellite. It's a ground-based experiment that will study the baryon-acoustic oscillations and structure growth. The key goal of DESI is to, exponentially increase our number of galaxies that we have, or galaxy catalog. So previously, in the latest experiment, we had about 2.8 million galaxies from SDSS 3. DESI was planned, let's say we started about 4 years ago, but DESI was planned to obtain about 30 million galactic spectra, extragalactic spectra. We are 4 years in, about 4 years in, and we already have 48 million. So DESI is outperforming its expectations, and we already increased an order of magnitude our samples. So how do we do it? So this is the diagram of what the telescope looks like, the DESI looks like. So, okay, this is the focal plane. Light goes up here. There is a mirror somewhere here. It bounces off the mirror, comes back into the cylinder tube. This is the focal plane. And on that focal plane, we have robotic positioners that figures out where the galaxy light falls on and automatically adjusts itself. And we have about 5,000 of those. What this enables is that when we change our position in the sky, we can automatically rearrange the entire focal plane and start observing and collecting data. And this is what this focal plane looks like. It has about 10 slices. Let me go back. So this light goes here, then it goes down to the spectrograph. We have about 10 spectrographs. So there are 10 slices here. And each of these are the robotic arms that can move. Okay. So what we're going to observe is, what we're trying to measure is the baryon-acoustic oscillations. So initially the universe is a hot plasma with protons, electrons, and photons are tightly coupled. What this does is this blue line and red line, if you can see, is that the photons and gas move together. If there's a big overdensity, this gas pressure, the radiation pressure pushes it out, forms a spherical wave. But this travel speed is about universe timescale. Once the gas cools and forms neutral hydrogen, now the photons are not coupled to the gas anymore. So that's what happened here. The gas now lags behind, photons freely stream out of it. But now we have a characteristic scale about 150 megaparsec. Now gravity does its job, where the dark matter falls into this overdensity and baryons goes back to the original overdensity. But nevertheless, this characteristic scale remains in the universe. And that is called the baryon-acoustic oscillation as a standard ruler. And if you look at all the pairs of galaxies or of all the pairs of matter, you'll find an excess probability of observing a galaxy at that separation. Of course, that was one spherical wave. This is a three-dimensional movie. So you have this spherical overdensity. So you have an overdensity and creates this spherical wave that goes out. But we don't only have one, we have multiple of these, like you can think of the raindrops. So all of these will be interfering with each other, right? So that's the pattern you see. So that's the initial imprint, the characteristic scale that's formed by early universe physics. Okay, this movie is a little slow, but then the structures will preferentially form in these regions. So these dots are actually galaxies. So every galaxy preferentially forms or occur in these regions. Again, this is a bit of an exaggeration. The universe actually doesn't look like this. It's not this obvious. But each of these dots are actually a type of galaxy. Then what you do is you look at all the pair separations. You pick two galaxies, measure its distance, add it to your counter. If you do that enough, and if you do that many, many times for millions of galaxies, you'll see a clear signal in the separation where the baryon-acoustic oscillation happens. There's an excess probability in this clustering. Okay, let me move forward. And also, let me also introduce the line before us. So galaxies are distinct objects. They are tracers, like point-like tracers. But the universe is not empty. If there is a light coming from an object, the intervening gas will absorb it and form absorption lines in the spectra. So in this case, this is a big quasar. It's a black hole accreting mass, and it radiates this spectrum. And as this light goes towards us, it will redshift, so the entire spectrum will just redshift to the right. But as it redshifts to the right, this entire spectrum will hit some gas in between us and the quasar. And those form the absorption lines. Okay, so we can use those absorption lines. So this is the static image. So if you this is an actual data from DAISY. If you look at the quasar spectrum, this is what it looks like. There's a big Lyman alpha emission peak because it's a hydrogen gas accreting around a black hole. That's what it radiates. To the left, you see this absorption line, and we use these lines as a way to trace the matter. What we can do is similar to galaxies. We take all these, so this is a quasar, this is us, this is the gas between us. Take all these absorption lines and correlate them. If you correlate them or make this correlation function plot, you again see the baryon-acoustic oscillation feature. Our two results, the DDR2 results, are published in these two papers. I put them as reference here. It's a couple of months old. I think they're just starting to get accepted or getting the referee reports. If you look at the expansion history of the universe, so this is the age of the universe on the x-axis, starts from a singularity, let's say, or CMB. Then we go to the present day, and this is the size, which becomes 1, rescaled to 1 today. We can measure this baryon-acoustic oscillation scale in two directions. If we are the observer here, we can measure it across the sky, or we can measure it along the line of sight. So across the sky is alpha perpendicular, along the line of sight is alpha parallel. If we measure it across the sky, we know the sun horizon, the BAO scale through our physics, so we can figure out how far that point is to us. That's dm, the distance from us. And it turns out the line of sight gives you the expansion rate, the Hubble parameter. And we can do that for many, many different types of galaxies or extragalactic objects. These are short for bright galaxies, luminous red galaxies, emission line galaxies, quasars, and this is lime of a forest. So we can map the size of the universe across various time scales on both, and you can see this here, or you can see this here as well, as a redshift. Our big results was the fact that we had a very strong hint that the dark energy is not a cosmological constant. So there is an equation state. We can write an equation state for dark energy. Pressure equals to energy density times some factor W. W is a function of time, or scale factor, in this case, A, which is between 0 and 1. In the beginning of the universe, A is 0, today is 1. So it's just parameterizes the expansion. And if dark energy is cosmological constant, W is -1 throughout the time. But a common parametric model is that, let's parameterize it as a constant plus some time evolution. And on the right, again, we're mapping the BAO scale throughout different times, from lime of a forest, different quasars, ELGs, etc., etc. The flat lambda CDM, so the cosmological constant called dark matter paradigm, is this black line. But our data seems to prefer a relaxation of constant dark energy to some evolving dark energy. So W0, WA plot here. So as you can see, the data points goes better this way. And we can also make a confidence plot of this WA, W0. Because in this axis, again, W0 being -1 and WA being 0 is a cosmological constant. This is this point. The BAO itself doesn't really rule out the cosmological constant, but we have to combine with other data sets. We combine with CMB, first of all. That's the best way to actually scale the BAO itself anyway. That gives us a 3.1 sigma deviation or tension with constant lambda. So this is this dashed line here. The other data sets are the supernova data sets. There are 3 different surveys. They're all equally good. There's not one better than the other, so we have to do all 3 combinations. So Pantheon Plus, Union 3, and DES Year 5 are all supernova experiments that measures very nearby supernovas and measure the distances. Each of them gives slightly different preference. For W0 WA, the highest one being DES Year 5 supernova. So that's our main results. I had a few more things, but I think I'm going to stop here. Maybe I can take one question if there is time for questions, but otherwise I have to go. Thank you.
We thank Dr. Naim Göksel Karaçaylı for his insightful contribution to the Feza Gürsey Commemoration Day, held in collaboration with Boğaziçi University, Middle East Technical University, and OSTİM Technical University. So if there's any question now, we can have it. Okay, I believe there is not. Thank you so much.
Thank you.
Today we proudly honored the legacy of Feza Gürsey, a towering figure in the world of science, on the 33rd anniversary of his passing. During this meaningful commemoration, we had the privilege of hearing from distinguished speakers on some of the most pressing topics in modern science. We sincerely thank all our speakers for their valuable contributions and all participants for their being part of this special day, and Boğaziçi University, Middle East Technical University, and OSTİM Technical University for their kind collaboration in making this event possible. With the hope of carrying Feza Gürsey's inspiration, scientific vision into the future, we wish you all a pleasant evening.